It's okay. Okay, let's get started. I am Javier Romero. I'm a co-organizer of this Virtual Try-On CVPR 2024 workshop, together with Vidya, which was one of the main persons organizing this, and she couldn't be here. I would have loved her to give this introduction, but she's here with us in Zoom. Sunil, Katie, and Ala, who is not here, I think, and Richard. My job is to entertain you for something like 10 minutes. I mean, thank you for being in time, but just in case people show up a little bit later, I'm gonna give you a couple of strokes of Virtual Try-On for the next 9 minutes. So Virtual Try-On, we wrote in the workshop that this is the first Virtual Try-On workshop in CVPR 2020, or in CVPR in general, which is extremely surprising. This is from 2010, and already there were things before.
Your magic, then check out Macy's Magic Fitting Room here at Herald Square on the main floor.
2010, people were already doing magic mirroring, and I mean, it did something.
Magical mirror that bridges the gap between the fitting room experience and the social web. Shoppers get to try on clothes via a full-length interactive mirror.
Look at those things. People would go into a room in Macy's, they would take a picture of themselves and then swipe through different garments to try it on themselves. So the world has advanced, but in reality, in terms of, well, sorry, this is how it actually looks. It's very difficult to find images of this system in action. This is the web in 2010. People had long text and maybe one image or one video here and there. But basically, you take a picture, you kind of scale it manually, you try to pose in the same way as the garment, and maybe you get an idea. Well, this was 13 years ago. How has the world moved since then? In reality, very similar systems have emerged since then. I think this is from 6 or 7 years ago. This is a company that still apparently sells these kind of systems. You pose in front of the mirror, you do something, select some clothes, myself. Now, and ideally move this at least somewhere here. So trying glasses on yourself from an image that has also been around for a while, and this already for some years ago felt okay. You can notice that this is not fully real, but still it was getting there. And another kind of localized kind of virtual try-on is for shoes. This is from WannaKicks, which pretty early on, this is also 5 years ago or so, did a great job on emulating those 3D shoes on your feet, tracked with your mobile phone to show in real time how it will look on you. Some of these systems have actually hit like the big scene of being tried by lots of people in places like Amazon. I worked for Amazon for almost 4 years, a few years ago, together with people like Sunil. I think he will talk more about systems like this. The trying on your shoes in 3D is something that you can access in Amazon, in the Amazon store in your phone. You can try this with thousands of shoes. We also had a few things that, oops, this video is not playing. Well, yeah. You could buy t-shirts and see how those different sizes would fit on a model of your size. And there was also, we also worked on a feature that unfortunately is not available anymore, but basically we created t-shirts made for you, given a couple of pictures that estimated your body shape. Sunil, which is the second invited talk today, will talk a little bit more about these systems and more. If we go back in time, another person with whom I collaborated in Amazon, Ming Ling, had this incredible paper, which blew my mind. This is 2016, and she was estimating the patterns of clothing from single images, if I remember correctly. So Min Ling is our third invited speaker today. And probably she will, I don't know if she will talk about this or other things, but this has been a remarkable paper to have kind of as a goal to actually achieve this at scale and with multiple garments and all that. Like getting garments that are simulatable from single images is still a challenge today, 7 years later after this. But in reality, something that blew my mind also a couple years ago, no, 1 year ago, something like this, was, well, 1 second about that. What I wanted to say in this slide is that in terms of commercial systems, this system from Google is also available today. This is something in which you can try a particular garment in 40 different models of different sizes. And this runs, it's super realistic. We are not at the level of, oh, I try my glasses and they kind of look okay. This to me is fairly convincing, super powerful. And good news is that this system is based on a system that was already released as a paper a couple of years ago, and there's a new paper coming this year from Ira Kemmelmacher and Ligan Zhu from University of Washington that achieved with diffusion these kind of systems, basically these kind of results. You see in here folds, tucking in your t-shirt or your jumper inside the trousers. This is at a different level from the Macy's kind of system that we saw before. So all this to say, these are super exciting times to actually start seeing garments tried on different people that look realistic. This system, one of the things that enabled this was a huge data set of images. And I'll take that as an opportunity to tell you that actually tomorrow we are presenting a small data set, but high quality in a different workshop. This is the social present with a Kodak Avatar workshop in Summit 333, 9:30 a.m. One of the things that is relevant, apart from all the things that we're creating with this data set, is releasing scans, images, and lots of different assets for different people with normal clothes and minimal clothing. So if you want to reason about what is the relation between clothes and the underlying body and explore problems that connect those to mobile phone data on other captures, this is a good place to start and see other talks that are based on this data set. With that, I've talked about the second, third, and fourth talk, Sunil, Ming, and Ira. And the last thing that I have to do in this, actually, I'm just in time, is talking about Gerard, who is the actual person that is going to speak now. Here I put together a very old but cool work from Gerard, Cloth Cap, TaylorNet, and Sizer, which have reshaped the space of virtual try-on. Gerard is a professor in the University of Tübingen. Before, he was a group lead in Saarbrücken and postdoc in MPI PS. And I mean, he does many more things apart from dealing with clothes and virtual try-on. But yeah, we are looking forward to your talk, Gerard. Thank you. Whoops. Now I have to mute myself, probably.
Good, right? Yeah. And I will share desktop one. Okay, now let's do a Zoom check. Can the people in Zoom see the presentation? Yeah? Okay, good. All right, good. Then let's get started. Yeah, so for today, like the title of my talk is what do foundation models know about 3D humans in clothing? So in my research group, we work on different areas, not only on humans in clothing, we work on basically modeling the appearance of humans. This means the geometry and the texture. And so basically in this area, we're trying to make avatars that look indistinguishable from us from an appearance perspective. More in recent years, we became interested also in modeling the behavior, so modeling like how humans interact with the 3D world. So here we want to mimic like, this part of intelligence that is about understanding the world around us and interacting with it. And finally, we are also looking at general 3D scene and object representations. And so for these two last topics, I will talk about this tomorrow in a workshop on egocentric tracking. But for this workshop, I will focus only on the first part, which is modeling human appearance. So for this talk, I I want to like poke into this question of how much do foundation models know about 3D humans in clothing. But before I get into this topic, I would like to give a little bit a historic perspective focused on the research that we've done in my lab, but I think it's also echoed by the research done by many other labs. So essentially in 2015, there was the simple model, which is a mesh-based statistical model, which has been widely used and very useful. And this was based on basically learning from scans, like a mesh-based model that deforms according to pose and shape. And then we wanted to add clothing on top of that. And we worked on cloth cap, which is basically adding a layer of displacements on top of this simple model. And it was the first layered model on top of clothing, so we had to separate the layers. And it was also mesh-based. It had a lot of limitations, but this was basically some of the first steps in this direction. Then in 2018, we basically said like, well, okay, we have now this displacement-based model. We can model clothing to some degree. Now, can we get a video of a person rotating in front of the camera and reconstruct an avatar not based on simple, but also including the clothing and the texture? And so I will talk a little bit about this. And this was, I believe, the first demonstration that this was even possible. Then in 2019, 2020, there were like this wave of neural implicits and neural field models. And then people in the 3D human community also jumped into it. And it presented new advantages. And I will talk a little bit about this. Basically, you could model like wrinkles and layers in a nicer way, and you had like the ability of choosing the resolution at test time, which you cannot do with meshes. But then like NERF appeared, or I should say like, before BIFO was seminal work, and then people were very excited because you could get like really high detailed like 3D models from single images, and it also seemed to generalize quite nicely, although it was trained on little data. But then NERF came about, and then you could get like very photorealistic results, but then the focus switched more from generalization to basically subject-specific models that were looking super good. And we basically lost a little bit this interest in generalizing to all types of clothing and so on. Then in 2021, people realized, okay, these neural implicits, like these neural field models, they are not so easy to animate like, the simple model. You cannot change the shape, we cannot change the clothing. And so people worked into making these models more editable, right? And including some of our work like Simplicit, which allowed us to add layers on top of the simple model based on these neural field models. Now, Gaussian splats came only last year. It seems like 3 years ago, but it's only last year. And we're seeing a similar trend, like people are jumping into it for modeling humans. And then people are trying to combine it with simple, like making them editable, like giving the ability to layer those Gaussian splats on top of the simple model. So I would say over the last 9 years, we've seen a lot of focus on representations, not so much focus on data, at least at the research side, right? The industry is probably different. And now, like, the question is, like, what happens 2024 onwards? I think, like, there will be much more focus on, like, data and, like, poking, like, foundation models to extract the, like, 3D shape priors, such that we can now generalize to, like, different types of clothing, different types of poses. And I will talk a little bit of, like, some work that is fresh from the oven, which is human 3D diffusion. But before I get to this, like, I want to give, like, this historical perspective, because I think it's useful to know where we're coming from. Okay, so I believe many of you are familiar with the simple model, or have come across it. So this was basically a mesh-based model learned from scans. And basically the idea is to learn a set of displacements on top of a base mesh that model the shape deformations with shape blend shapes, and they are parameterized with these beta parameters that control the shape. And then you have the pose blend shapes that model how people deform when they change their pose. And then finally, you apply this set of, like, articulated transformations in order to obtain a mesh that should resemble a real human, right? And with this, you can animate people, and you can use it for many applications. Now, the question was, like, okay, how do we add clothing on top of simple? And we're still basically facing this problem. And back then, like, what we thought is, like, let's do the easiest thing that you could imagine. Let's add one layer that, similarly as we did for modeling the shape deformations, for example, we can model, like, clothing, right? And so why not add these displacements on top of the vertices such that we can model clothing in this way? Like, you start from a minimally dressed person, and you can add the displacements to basically model this clothing layer. Okay, but just adding displacements does not separate, like, the different garments. And for applications like virtual try-on, this is indispensable, because you need to be able to take one garment and move it from one body to another. So we needed some sort of segmentation, but we didn't want to depart from these, like, nice properties of the simple model, right? That is, like, these parameterized vertices. So our idea was to register, like, the clothing to the body, such that we had this, like, one-to-one correspondence. And then we could do, like, simple operations like linear algebra with clothing and bodies, if you will. So we could take, one clothing garment and subtract a body shape, and then obtain these displacements and apply these displacements to a new body shape in order to, synthesize this virtual try-on thing, right? This is based on registration to the body and then applying displacements in order to synthesize garments on top of new bodies. Right? No learning here. It's just taking the clothes of one person, subtracting the body, and applying these displacements to a new body. That's easier said than done. But the results were quite compelling, given that the method was relatively straightforward. But of course, like, we needed a 4D scanner, and this is hard to scale, right? And so this was a bit limited in that sense. Okay, so we thought, like, can we just get, like, a monocular video of a person rotating in front of the camera and reconstruct an avatar, including the clothing layer? And here, like, I simplify the method. The method was more sophisticated than this, but the basic idea is that we would optimize the pose for each of the frames of the person who was basically rotating in front of the camera, and a single shape and a single clothing, assuming that the clothing does not change over time, right? And basically, the idea is to optimize those parameters in order to minimize a distance. And this distance is measuring the discrepancy between the rendering of our model, M, which is the simple model with the displacements, and the images. And then basically, you would optimize these and obtain, like, the 3D avatar. And these were the results that we were obtaining. This was CVPR 18. I believe this was the first time that we demonstrated that this was even possible. We were quite excited about these results. Now, I mean, there's a lot of artifacts, but yeah, this was basically the first time that then people said, oh, this is even possible. And then there were a lot of methods coming after this. Of course, this method, however, is just, as you've seen, like only a layer of displacement. So it's not separating the different garments. And so for virtual try-on applications, you need to separate the garments. And so in this work, which was a follow-up work, it's called multi-garment net. We basically have displacements that now are segmented so that we can separate the different clothing garments. So you could take a jacket of a person and synthesize it on top of a target subject, like you can see here. I will not explain the details, but the basic idea is to have a neural network that will predict each of the garments which are registered with the body and the body separately, and then you would assemble these pieces together and render these against the images and then compare losses based on segmentation, masks, and images. And we also had like a bit of 3D data and a bit of 2D data, and we trained this thing together. Now, this goes very quickly, but it's just to give you a little bit of a broader perspective. In terms of virtual try-on, also, we had this idea of like, there's a lot of clothing images on the internet. So can we like lift these clothing images to the avatars? And this is what we presented at CVPR 2020, which is based also on geometric warping and so on. So if you're interested, you can also have a look at these like older papers. All these works were mesh-based, right? And then in 2019, 2020, there was this switch towards neural field models. And I want to give like a very brief perspective on what happened in this space. So basically, neural field models are based on modeling the surface as an implicit surface. So you have like some function that takes points P from R3 in 3D and predicts like a distance, for example. And then the surface is basically all the points that satisfy the condition that the distance is 0. It's the 0 level set of the surface. Now, why would you do this thing? Well, the cool thing is that the neural network could be trained to predict per point. So you could, at test time, choose how much resolution you get. And this was very convenient to get like these wrinkle details that actually matter in modeling clothing. However, these models were not animatable, right? You could not change the pose, which is something very interesting. Like for virtual try-on, for example, you want to see like, how the clothing like will move as I move, right? For anything that has to do with animation, you need to be able to see how the clothing deforms as a function of motion. And basically, our solution to this is like based on what are called generalized neural implicits. So the idea is to warp the underlying space where you evaluate this function f. So basically, you have to start from the deformed space and then apply the inverse transformation, g minus 1 plus delta p. So basically, if you have to rotate and displace vertices, you have to apply the inverse rotation and the inverse displacement, and then evaluate this warped space with the same function as before, and then you could train this end-to-end. What was the result? Like we could get like cloth deformation as a function of pose, which looked very detailed, like what you see here. This is an example of the synthesis of the model, which looks more like a scan than actually like a model. And this was quite nice because you could see like, this layering of the jacket and so on. This would have been almost impossible with meshes. So, so we were excited. People were like happy with this. However, like this is hard to render. It's hard to obtain meshes from this because you need to run a technique that is called marching cubes, which is slow and it's tedious. And one additional problem is that over time, those meshes are not having the same parameterization. So you don't know, what vertex corresponds to the shoulder, what vertex corresponds to the edge of the clothing, which is necessary. For example, you want to texture the garment. So this is not very convenient. So we had a solution last year for this, which is called neural surface fields. And it's very simple. And maybe this idea like is applicable to other domains. So the idea is like very simple. Instead of like poking every 3D point, R3, and predicting a distance, You just start from like points on the surface of a simple mesh, for example, of a smooth surface, and you predict for every point on that surface, you predict the displacement. That's it. And so basically, you can think of this as a continuous version of these displacement models that I was showing, like cloth cup and so on, where you had displacements that were bound to the vertices. Now they are bound not to the vertices, but they are bound to the surface. So for every surface point, we can predict the displacement. And the nice thing is that, we could like change the resolution at test time, because you can change the resolution, you can subdivide the simple model and then query the neural network at all these vertices that you want, and then get like arbitrary resolutions at test time. So you could also animate, this is my avatar, like dancing as I would never be able to dance. And this was basically like also modeling these cloth deformations. Okay, so this was a super quick, I believe many of you are lost, but it's fine. I just want to give you like a bit of perspective. As long as you got a little bit the gist of things that have happened, that's enough. But basically, like to summarize these 9 years, I didn't cover like Gaussian splat papers, but I believe there's many at the CVPR. I think like the main problem of all these methods is that maybe there's been too much focus on the representation, which is very important. We should continue working on this. But maybe we have forgot that, like, we're training on small scale data, maybe just a few thousand scans. And that's not sufficient for really generalizing to multiple types of poses and clothing. And so maybe we have like not looked at this enough, right? How to, maybe because we didn't have the tools also. Now we have like these foundation models, we have an opportunity to poke them, to use them as strong priors. This is where I want to focus on this second part of the talk, which is basically a new model that is called human 3D fusion. But there's other models that are coming up based on text-based avatars and whatnot. And here the basic principle is like, how do you poke these foundation models in order to extract 3D information? So this is realistic avatar creation via explicit 3D consistent diffusion models. And the goal here is well-known goal in computer vision, which is like single image 3D avatar reconstruction. The input is a single image of a person, and the output is like a 3D reconstruction of the person, where we want to obtain like also the texture, including like geometry for the back part that is occluded. These are results from the model that I will present now. This model is based on diffusion and also based on Gaussian splats. So this is the input and this is the output. And here we're showing the Gaussians that are underlying the model. We can also obtain a mesh, and we can render, using Gaussian splatting, we can render this mesh from different viewpoints. And what I'm quite happy about is that if you stop here, for example, this part is completely occluded, but we still get like these nice wrinkles and this nice completion, although this is not seen in the front, right? This is something that not even the strongest models like BIFO could do, right? I think for this, you need really to have a bit of a probabilistic model, which diffusion has. So this works for different types of, geometries. That's something that, for example, like with these mesh-based displacements, you would never be able to reconstruct this because it's very difficult to model this type of geometries with displacements. It's also very difficult to obtain this kind of generalization training on a few thousand scans like we've been doing over the last years. All right, so I think I don't need to convince this audience that like modeling 3D humans is hard. You have like variation in body shape, you have texture, you have clothing types, different topologies, different geometries. It's basically a zoo of things that can happen, right? Now, we had these foundation models, which could, for example, take an image of a person, XC, and then take this noise and basically obtain a new view of that person, right? This is a new view of that person. This is basically a result of stable diffusion. Okay. Then people said like, okay, let's go further and let's predict multiple views of the person. Like in this case, it's like 4 views. And it's astonishing how well this works. And you could argue if you have many views, you could argue that these models really understand 3D. If I have any possible view, I would argue that's the same as 3D, right? I can render from any viewpoint that's the same as 3D. Now, not so fast, because the problem is like if you train a model to generate images, it's going to be very difficult that the model nails like this pixel alignment such that, you know, things are really 3D consistent. So what's going to happen in the end is that, you know, each of the images will look fine, but if you would triangulate things, the feet would not match, the hands would not match, so things would not be 3D consistent. So we have to bring some of these old ideas, like which is basically having a proper 3D representation into these large-scale models. Okay, so the first idea you might have is like, okay, let's take these inconsistent views and then reconstruct like a NERF model or an SDF or a Gaussian splat or whatever, right? This might be like a reasonable thing to attempt. However, this is too late. The damage has been already done because the views are already inconsistent. And when you try to do this, you get like these halo virtual humans where you have like, you know, by reconstructing things that are inconsistent, you get a 3D reconstruction, which is not really consistent. Also, you get blurriness and so on. So if you ever try to reconstruct things from badly calibrated views, you get these same effects. So what is the underlying problem? Like the underlying problem is that the multi-view is already inconsistent. So we need to fix things earlier on. How do we do this? So when we look at the diffusion process, we start from xt and we take a series of steps until we get to x0, which is the signal we want to recover. In each of these steps, we have a result that is multi-view inconsistent. And there is an equivalent, or you could think of a manifold of proper multi-view images that come from a real 3D scene or a real 3D avatar. So our basic idea is to, at every step of the diffusion model, to project back to the manifold. That's the basic idea. You basically take one step, project to make it consistent, one step project to make it consistent, and so on, okay? How do we project to these green dots? Well, this is where the 3D reconstruction comes into play. So we have 2 modules in this model. One is a 3D Gaussian splat-based, which is reconstruction, which is called render diffusion. And the other module is what we already know from other papers, which is the 2D multi-view diffusion model, right? And the important thing is to synchronize these 2 guys at every step of the denoising process, such that we use the 2D multi-view diffusion as a strong prior for the 3D Gaussian splat reconstruction. And at the same time, we use the 3D reconstruction, we render it, and we use it as a strong prior also for the 2D multi-view diffusion model to guide it towards producing views that are actually 3D coherent. So this is how we implement, this is how the model looks like. There's a lot of moving pieces here, so let me guide you a little bit. On the bottom, you have the typical diffusion where you start with the noisy signal and you denoise until you get the signal that you're interested in this case, like the 3D Gaussian splats. Okay, this is like each of the steps. What you would do is like doing it image-based, right? You have noise and you denoise it until you obtain an image, right? Now, our key idea is to not denoise based on images, but denoise lifting during the process. So how do we do this? Now, let's look at one iteration step, right? We go from xt to xt-1, and we zoom in, and this is this blue box that you see here, right? This big diagram, okay? So we have these 2 components, the 3D generative model, G, and the 2D multi-view diffusion model. And how this works is like, in a given time iteration, we have the input. This is the monocular input view, and we have the monocular, like the noised images at this current step. Okay, these are the noised images at the current step. We want to denoise these images. Now, we send this to the 2D multi-view diffusion model, and it obtains some estimate at this current estimate. It's not perfect yet because we are still denoising. We send this estimate of the 2D multi-view diffusion into the 3D generative model. And I call it 3D generative because it can produce multiple solutions. And we also send the noisy views as well as the conditioning. So this model swallows, if you want, like 9 images, the noisy and the prediction of the multi-view. And it produces like the Gaussians, which are the Gaussian plots, which we then render, right? And here comes the interesting part. We render and we have like a rendering loss, and we backpropagate through the 3D generative model and the 2D multi-view diffusion model. So these two guys are learning in tandem, right, together. So how this would work, you would obtain these views, then you would add, you know, the noise, this is iteration t, then you would add the noise corresponding to iteration t-1, and then these guys would go here, and then the whole process would start again. Okay, that's how it works. And so this is like, I find it conceptually very appealing because the two things are like, you know, talking to each other, you are verifying your solutions during the iterations, and it's not like you just use one model and then combine too late, right? It's the kind of, it learns to fix itself. Now, this is trained with a lot of data, right? This comes from stable diffusion. So this is providing a very strong prior, which might be incoherent, but it's by doing this process, this back and forth, it learns to be coherent. So the message is that the 2D multi-view diffusion model and the 3D render diffusion, they basically help each other. The 2D MVD, so the multi-view diffusion, provides a strong multi-view prior, helping 3D generation, and vice versa. The 3D model provides a 3D representation, which refines the multi-view consistency of 2D MVD sampling, right? Right, so the 2D multi-view diffusion model and the 3D render diffusion are synchronized at each time step so that the 3D model benefits from 2D multi-view, and the 3D model guides the multi-view diffusion process as well. You can check the paper. We have a lot of comparisons with prior work. Let me like show you a couple of examples. So for example, like comparing to Baifu, for example, like here, notice this guy, like, you know, it predicts like the hat on the back correctly, whereas Baifu, like it predicts like a face, so it incorrectly predicted the face where it should be a back. If you look at these like wrinkle details, like are much better at the back region. Like if you compare to Baifu and other like more recent methods like whatever, Instant Mesh and Saifu and so on. I don't have time to go into all the details, but we have evaluated this also numerically. We also compare to the most straightforward baseline, which is I take the multi-view diffusion and I do a 3D reconstruction, and the results are significantly better because, as I said, you can just not recover the errors that late on the pipeline, right? So if you do 3D reconstruction after multi-view diffusion, you have like these halo effects, and then basically have like this kind of avatars that are not sharp. Okay, now let me show you a couple of results. So this is the input view, and this is the obtained 3D reconstruction, where I will stop it here. Notice how like we get these nice wrinkles and completions for the part that is not visible. And I would say the level of detail is like comparable on the back and the front, which was always very noticeable in models like Baifu, where you had like very sharp details on the front, but really blurry results on the back. I think that's also by virtue of like this probabilistic nature of the diffusion process. Here's another example where the model hallucinates like a texture on the back, which is more or less coherent with the front. And what is nice, what I find most exciting about this work is that it wasn't really trained to generalize to humans and objects, for example, but you just throw like a human and an object to the model, and it produces something that is very plausible. So let me show you a couple of more results illustrating this. So you can reconstruct kits also, which would have been a problem with simple based models because they basically they cannot scale. It also reconstructs to people, although we never trained to reconstruct to people. So to me, this is showing that the model is really learning something useful. It's not just overfitting to the data, but it's actually learning something useful. It's not perfect. So if you stop here, this is like a little bit of a failure mode. Let me show. Like this mom with the kid, like the faces sometimes look a bit flattened. It was never trained for this, but I noticed that I need to show that result. Where was this? Oh, cannot find the mom with the kid. Here. Yeah, so when it rotates, I notice you see that the geometry is not perfect in this case. But nonetheless, I think it's quite nice and quite remarkable, like the generalization that we obtained with this model. All right, so we gained, like now we have good generalization. I'm now very convinced that the foundation models, they do know a lot about 3D. They are not 3D consistent, but they do know a lot about 3D. There's an opportunity to compensate for the lack of 3D data that we always suffered from. It's probabilistic, which is nice. We also have in the paper examples of sampling. It's not like the diversity is not amazing, but there's some diversity. We still suffer from there's no layering, there's no control. So it seems like the story repeats itself. I guess people will jump and try to make these models also like animatable, also layerable, and so on. There's some work to be done. Maybe for this, we need to revisit old ideas. We need data for this. Like always, you need to take foundation models and fine-tune them on a bit of data. So this is the data set that might be interesting for doing this, and maybe some of you find it interesting. So basically, we are releasing here 3,000 scans with 18 clothing classes. This is a data set that is called Closet. And basically, we made sure that the segmentation of clothing was accurate, and we have a model also for segmenting clothing and also an interactive tool to fix errors. You might check that out if you're interested in modeling clothing segmentation and so on. Yeah, so these are results with this model that is called Closet, where we get like segmentation of scans into layers. So maybe we look at this and combine it with this like foundation models to get layers also. It would be cool. All right, and I think I'm not doing so bad in time, so actually I'm a bit too fast. So yeah, and let me just very quickly now show you the papers that we will present at CVPR, like just an overview, not go in detail, but because maybe you find them interesting, and we're happy if you come and talk to us and like to my students especially, that would be cool. So the first paper is an RDF. So this is neural Riemannian distance fields for learning articulated pose priors. So basically it's a pose model. That's oftentimes we need to constrain the pose so that it's plausible. And this is a continuation of the pose and DF work. And we figured out that we did a lot of things wrong. And now we're doing it much better. And the model is also, in consequence, much better. So for example, like you can do inverse kinematics and or probabilistic inverse kinematics. So basically you can give this, you can ask to fit a model to these markers, for example, right? And then you can use this pose prior to constrain the pose to be valid. Otherwise, things would go astray. And here on the left, we show like a model that is widely used, which is VPoser, which is based on a variational autoencoder. And on the left, you see that the variational autoencoder always produces the same result. That's kind of well known, that typically happens. And with our model, we can, produce different solutions. I cannot go into the details, but basically it's strong prior, which can model better like these tails of the distribution better than VAs. If you're interested in that, then come to our poster. We also have a model that is maybe more related to the topic of this workshop, which is painted. So here we produce textures given meshes. So given meshes and text, we can texturize the meshes. So you can say like paint this mesh with whatever texture you want. And then we have like an SDS based loss that propagates this texture into the mesh, and also we have physically based rendering so that we can change the material properties and the lighting and so on. So you have here the meshes, and then basically with text prompts, we can like paint these meshes automatically. So another example of using a foundation model to, extract 3D information as well. So notice how, the model already learns to put like the right, for example, like the right continents, the right, the right texture at the right geometry parts of the object. So which is quite nice. We have work on modeling behavior. So this is template-free reconstruction of human-object interaction. And so here the idea is to generate procedurally lots of human-object interactions, like using some heuristics and some optimization. We can basically like do data augmentation and produce a lot of different interactions of humans and objects. And then we train a model, and then we can, from single images, reconstruct human and object. So that's something that I also find really cool. You can also come talk to us at the poster. That's also something that we will see more and more, this procedural generation, like and learning from synthetic data. That's something that we should also take seriously, I think. We also have work on modeling hand-object interactions, gears, and basically here, given like a wrist trajectory, we synthesize the hand's motion such that it grasps objects and so on. All right, so now I come to the conclusions. So I've shown a little bit of a historic perspective. I know I was very fast, but hopefully you got some gist of how the field has evolved over the last 9 years. So avatar models evolved from meshes to implicit surfaces, and now Gaussian splats. That's the evolution that we've seen. Regardless of representations, I think that we have been training on small-scale data for perhaps too long, and maybe that now it's the time to change that because these models didn't have very strong generalization capabilities. Data in 3D is still scarce, and foundation models can serve as a strong 3D shape prior. We've seen that foundation models do know about 3D, but typically produce multi-view images that are not coherent. So like nothing beats a 3D representation in my view to obtain 3D consistency. Presented human 3D fusion, which couples multi-view foundation models with generative 3D reconstruction to obtain a native 3D representation while they're leveraging large-scale data. And I think future work now should address control over the reconstruction, being able to animate these reconstructions, being able to layer clothing, maybe transfer garments from one person to another. I would like to say thanks, especially to my team. Unfortunately, they got a bit small here, but they deserve all the credits. So all the credits go to my students. It's really formidable to be able to work with such team of talented and yeah, very, very, very good researchers. And thanks to the sponsors. And basically now we try to put all our software online, so you can take a picture of this QR code if you're interested. There we have all the data sets and software of the models that we publish. And now I'll be happy to take questions. Thanks.
In the 3D diffusion data, human diffusion, 3D diffusion data, I think I'm changing very specific to humans, like on prior specific to human. Is it like a generic method like training?
Yeah, okay, maybe I went a bit. So we fine tune. So we start with stable diffusion, right? And then so the multi-view diffusion is fine tuned on Objaverse, which is based on objects, and we fine tune on a bit of humans, and that's where the prior comes from.
How fast is this pipeline, and what do you think about this kind of like foundation-based method eventually display high-HD like different data?
So the first question is how fast is it? It's I don't know the numbers now. I should check. It's in the paper, but it should be comparable to Stable Diffusion, like at the same time. So not much. So training is longer, but then the test time is fast. And then the second question is like, can you repeat, please?
The human free diffusion is a optimization-based method.
It's not. It's diffusion-based. There's no optimization. It could help to add a bit of optimization. It always helps to add a bit of optimization. Here we don't have. But actually, I see a lot of parallels between diffusion and optimization in the sense that it's not a one-shot prediction, but it's like iteratively getting to the solution so the model can verify its own prediction. So in that sense, there's an argument to be made that there's some connection between diffusion and optimization.
This one would better help exploring this foundation model.
This one or which is the other? Well, the PyFo-based method does not leverage any foundation model. The PyFo-based method is trained on like I think 4,000 scans, and it's basically making pixel predictions. So there is no connection with the foundation model there. Thanks for the question. Yeah, more questions.
The 3D human diffusion paper, were you interested at all in the metric reconstruction of the human, like the actual measurements of the person body parts?
Right, that's a good question. No, we're not so much focused on getting the metrically accurate. There's always like to fine-tune the model, we always place the humans at a given distance to the camera. And that's how we train. So then there's always this scale ambiguity. That's something we should maybe look into. But you could see that you can reconstruct kids and humans. Yeah. We haven't like metrically, I mean, we have numerical results using Sizer and other data sets. But we didn't look at this like, ability to predict metrically accurate. Yeah, but there's always this ambiguity. You don't know if you're close to the camera or big. That's Javier.
So very cool. I mean, the idea of having the 3D projection makes total sense in the 3D fusion paper. There is still a gap in terms of resolution detail between 2D and 3D methods. Do you think it is mainly computation that you need to put Stable Diffusion, Excel, based on visuals so that you spend forever to get everything? Or there is something more fundamental that when you inject the 3D, you're putting it away a little bit from the foundation model main expertise and you lose a little bit of precision, or maybe it's wrong. What's your opinion?
I think the bottleneck now is the resolution of the 2D multi-view diffusion. So if we had high resolution, I think we would get also high resolution. Yeah, so that's, sorry? I think like 128, something like that. Yeah, or 256, but I think most of the results are based on 128. Yeah, it's what this. Yeah, I think this will get better though. This multi-view diffusion, like, will get like at reasonable times, like higher resolution. So I think right now that's the bottleneck. It's a good question. I mean, we're also a bit annoyed about that we're not getting this high resolution you would get otherwise.
Okay, let's thank our speakers again.
Oh, that's more money. Thanks. Thank you.
Okay, we're gonna start our next keynote speech talk again with Sunil Hatap. Let me just click here.
Mic on, camera on. I should be unmuted now. Yeah, and we also have garment layering attributes, basically telling like what the garment should be laid out in the final trial results. And given all these inputs, the mix and match virtual trial system will try to synthesize the final trial result of how those garments would look on the input person, as well as following those like input layering attributes. For example, here the sleeve is rolled down and the top is tucked in the shirt. And due to the time reason, I want to basically quickly introduce two like important contribution of this work. The first one is mix and match is better at like rendering intricate garment detail, like very small text and logos compared to trial diffusion. So this is like kind of like this challenge introduced by the application itself, because now we are going from upper body trial to full body trial. So you can see the garment actually occupy much smaller area in the image. And if we directly apply trial diffusion to the full body trial, and we can see the text and the logos got like distorted and blurred out. But with the mix and match virtual trial, now we can correctly preserve and synthesize those small tags as I show in the zoom-in visualization. And the key contribution here we found is progressive like training strategy. So for the first stage, we pre-trained the whole diffusion model at a lower resolution from scratch on our like collected 80 million data. And after this stage is trained, this stage is basically learning low and mid-level structures and working. And after this stage is trained, we continue to train the exact same model at a higher resolution on the higher data with the same data. And this stage is basically try to focus on the high frequency details. And here's some like evaluation results of like progressive training versus training from scratch. We can see the detail is more better preserved. And here's more like detail here, like we can correctly synthesize that with very small and cluttered like text and logos. Another challenge like in the current virtual trial system is like the closing agnostic representation mainly cause a person identity loss. And we try to solve this problem like through the Dreamboat style fine tuning. And we mainly tackle two challenges here. One is how to acquire the fine tuning data. And the second is how can we fine tune the model without any like overfitting or inefficiency. So this leads to our virtual trial unit diffusion transformer called a VTO UDIT. So the general idea is just to disentangling the denoising from the conditional encoding. And we first basically encode everything to the latent space, and we have a conditional DIT to do the denoising, and finally we decode it to get the final image. And during the fine tuning, we just optimize the person feature and freeze all other components. So the final like fine tuning, we can reduce the space from 4 GB to 6 MB. And because we freeze the whole model, so there's like less overfitting, because like more like optimizable part are got like frozen, and the degree of freedom of optimization is quite small. And for synthetic fine-tuning dataset, we just pre-collect some person input, and we use the pre-trained model to generate the trial results. And this trial result becomes a garment input, while the person is the target image is the person in the ground truth, and it satisfies the fine-tuning dataset. And here's like more results of the person identity preservation compared to all the baselines. And here's more results like for like instruction like garment layout editing compared to all the image guided diffusion pipeline. And you can check more details in our paper and project webpage. Here's more. And we also show some like dress trial result for the full body garment. We can handle those like high like non-rigid like dynamics pretty good just by training on like large data set. Yeah, thank you very much. So if you have any questions, just take a look at our project website here. Yeah.
Okay, when next speaker is preparing, we may have more question. Yeah.
Why do you think this progressive training works? Because you're using the same weights, but the pixels are referring to different regions when you upsample on the training.
So progressive training works because you can see so at the lower resolution, the attention map is actually at a lower rate, so it's basically easier to learn. And when you train on the high data, basically the attention KV and becomes larger, but those learnable weights are still here. They already encoded some mid-level or low-level prior learning in this diffusion model, and all you did basically is just to using the prior here, only needs to adjust it a little bit. Yeah.
Okay. Thanks. Our next speaker is Xuliang Ning from Chinese University of Hong Kong.
Okay, hello everyone. My name is Xuliang Ning, and I'm from the Chinese University of Hong Kong. Yeah. Today I will introduce my recent work picture, the photorealistic virtual try-on from unconstrained designs. So now this is my outline. Yes, first, so this part. So for the problem definition, nowadays the virtual try-on becomes more and more popular in the area of online clothing shopping, and it's also active research of computer vision. So look at this figure. The first line represents the traditional virtual try-on. It aims to generate photorealistic visualizations of individuals wearing a retail garment. However, this constrained generation is limited, as the real online virtual try-on maybe need to like the second line. The constrained generation is limited, as the real-world online shopping behavior often involve a bit of design. So with the desire to mix and match the elements from different garments, like this figure, the second line. So if you want to try a garment with the same style as the figure F and the same texture as G, so in this case, the traditional virtual try-on algorithm fails in this case. So to solve this problem, we propose a new task named UCVTOM, which greatly relaxes the constraints. Enable user to specify the style via text prompt or a garment, and specify texture user for garment image or swatches. And even you can add a logo on the new generated images. So like this figure, in this figure, the orange box represents the style control, and the green box represents the texture control, and the blue box represents other design elements. Okay, so this is our pipeline. So due to the fact that we have no paired data, which means for a garment, we have no separate representation for its style and texture. So look at this pattern. For a pure color garment, maybe we can use a mask to represent its style, and a local patch, just a local patch to represent its texture. But how about this garment? We think that we also use this mask to represent the style, but we cannot any local patch to represent its full texture, other than the clothes itself. So, but if you use this clothes itself, it also can contain the style. So they are entangled. So to solve this problem, we design a two-stage pipeline. In the first stage, we generate a passing map according to the style, according to style condition, and we generate this passing map. And in the second stage, using this passing map and the texture condition, we can generate a new photorealistic human images. Okay, and another challenge is that how to achieve photorealistic texture transfer. So inspired from the fact that multi-level features is helpful for texture preserving. So here we use the hierarchical features in this clip encoder. And to reduce the computation complexity, we do feature clustering and choose one layer of features from each cluster. And another challenge is that the clip features is much useful for capture the stationary textures like the solid color, but it struggle with the non-stationary textures like the scale of the plate or the color distribution of this patch. So to solve this problem, we add a positional encoding layer before feeding the clip feature into UNet. Okay. And here we show some results. This is the style comparison. So we can see our model generates aligned images from the text description, the blue words. And here is the texture. We see our method can produce realistic human images with expected texture, like this one, this texture. Another important is that we can preserve the original garment style. Yeah, for this one. So here is our ablation study. We compared our two-stage model with one-stage model. We can see for this one, he can get correct texture, but he changed the style. The original style is short sleeve, and for this one, maybe he gets the correct texture like a black, but he also affected by the plate pattern. This is the style description. And for the right part, it shows the effectiveness of our hierarchical clip features. And another part is the effectiveness of this positional encoding. We can see it can capture the color distribution. For the B part, it is the upper part of A, and this is the lower part. So we can see, given different patches, we can get a different generated result. And for this one, it can get the different according to it can capture the skills. Yeah. Okay. And for the time limit, the time limitation, we just show our final result. We can get the fashion design. Yeah. For if we give different style, different texture, and other design elements, we can generate a different garment. Okay. So we will skip this part due to the time is limited. Okay. Thank you.
Yeah, maybe we have time for one more question. If not, maybe we can move on to the next speaker. Next speaker is Diffuse.
Am I muted? I guess so, yes. Okay, so hello everyone, I'm Diffuse, and today I would like to share our latest work, Gala, generating animatable layer assets from a single scan. The work has been done with my wonderful coworkers, Byungjun and Shunsuke and Hangbyul. So I've looked through the works in our short talk sessions and noticed many of them successfully enables the virtual try-ons in the 2D domains, especially using the diffusion models lately. In contrast, our work models humans in clothing in the 3D space, and which definitely has some pros and cons compared to the modeling in 2D. And I would like to explain throughout this talk. So as mentioned, our work is done in 3D. Given a single layer 3D human scan and a prompt for the target object, our model decomposes the input scan into the target object and the underlying human body. Important thing to notice here is that they are complete in geometry and texture and modeled in the canonical space, meaning the sizes and the poses are neutralized. Here's another example with the target object being the shirt. So considering the time, let me briefly explain a high-level overview of how Gala works. So given an input scan as in left, we first perform a 3D surface segmentation of the target object by lifting up the multi-view 2D segmentation achieved with the segment density model. We then remove those parts labeled as the target object, and finally complete the missing geometry and texture by leveraging the 2D diffusion priors via score distillation loss. Well, during this process, instead of using a vanilla SDS loss, we propose to leverage a post-guided SDS loss in order to correctly model the canonical shape of each assets. Well, it seems to be a rather simple process, but by applying the series of this decomposition and completion into the input scan, we get to generate multiple layered assets from a single scan. For example, starting from this input scan, we can first decompose the hat, next the jacket, and finally the hoodie and the gloves, which are all modeled in 3D. Interesting thing is that after decomposing several assets from each scan, what we can do is to compose those assets to efficiently generate novel 3D human avatars that are ready to be animated. As you can see, these assets can easily be consistently animated without undesired artifacts, which could be one of the strongest benefits of performing virtual try-ons in 3D space. In other words, performing virtual try-ons in 3D could allow for much better controls and then in 2D, such as changing poses of the humans, changing the rendering viewpoints, or enabling real-time renderings. Now, even if the sizes and the poses of the assets are neutralized in 3D, you might think that naively composing them would result in misalignments, and you are definitely correct. As you can see in the middle of figure in the middle, there happens to be those misalignments between the penetrations between the human and clothing when they're composed. So for those cases, we further refine the composition results via penetration handling by optimizing the vertex positions of the human in the 3D space, leveraging the fact that clothing should be on top of the human. And I guess this penetration handling could be another strength of performing virtual try-ons in 3D, since it is not that obvious for one to handle those occlusions in the 2D pixel space. Now I'd like to wrap up my talk with some additional results. Here we show some decomposition and canonicalization results of the leftmost input scans. Some more examples. As mentioned before, by iteratively applying our method, we can sequentially decompose the layered assets from a single scan. And note that we can also decompose a specific layer of clothing, the hoodie in this case, by recomposing the decomposed assets in the previous stages. Also, by using the recent 2D to 3D reconstruction methods, we can generate layered assets from 2D images. And as you might have guessed, we can also utilize any text to 3D generation methods to first generate the 3D human from text and then generate assets using our method. So this is the end of my talk. Feel free to drop by our post session on Wednesday morning for more results and details and try out our decomposition yourself using the release code. Thank you for listening.
So we are Our next speaker is Irene Jiang from Diffuse. Hello. Hello, maybe. Can you unmute yourself?
Hi everyone, my name is Irene from Diffuse. I'm office we do research and release products in the beauty virtual try-on domain, including makeup try-on, hair color try-on, etc. So first, a quick glance of how makeup try-on is achieved on web browsers due to privacy and bandwidth.
Your screen is with resume share, yes.
Yeah.
Can you stop sharing and retry? Share. This one. This one's fine. Yeah, working.
So due to privacy and bandwidth constraints on mobile devices, all the processing has to be done on the user's local devices. And often on web browsers, it is more constrained on computing resources. The existing pipeline first detect the landmarks on video frames and then apply a graphics-based rendering technique to achieve realistic makeup try-on in real time and in videos. And here's another example how we achieve hair color try-on, where we first perform a matting model followed by a graphics-based rendering technique. So on landmarks detection and segmentation already solved problems. So if we look at some of the SOTA method, they achieve amazing accuracy and have explored some of the efficient networks that can be run on mobile devices. However, real-world challenges still exist. Firstly, the speed. In academic papers, the profiling is usually done on the latest iOS and Android devices, but with real users, we need to achieve real-time, smooth experience with someone using 5-year-old phone and maybe with another 10 plus other applications open. So as shown here, the frame rate actually can ranges from 4 to 30 frames per second on a mobile net-like structure. And secondly, there are some wild Southeast data set, but the real cases can only be more challenging. For example, a user might be at home and have very dim lights, or the camera may be at low resolution. And lastly, the expectation of the accuracy in the real world will be extremely high. So to solve the mentioned challenges, we often work in continuous development. The beginning is usually specific data collection and annotation process, followed by quality analysis and of the collected data. And unlike the academic data set, the annotations are often obtained from multiple annotators to calculate the annotators' variance and the average labels. In the model development stage, model data will be also collected based on the error analysis. And then in addition to the usual metrics, the user perspective testing is also performed on the final end-to-end system to make sure any accumulated errors should not exist at threshold. Next, optimization such as quantization and other engineering techniques and profiling is also done before deployment. Finally, once the product is launched, user feedback will also be collected to help continuous model improvements. In a nutshell, data and speed are the two main topics in real-world VTO on mobile devices. So along these main challenges, we've done quite a few works over the last few years. First, on the data-related topics, we proposed the controllable CAN networks, explored controlled image generation by gradients based on a simple attribute classifier to gain distinct control. Followed by that, as SquareGAN, we propose a density correction in the latent space to achieve more disentangled control. And also in 2019, we proposed a landmarks detection framework that is 16 times smaller than MobileNet, and along a few other works trying to speed up GAN, visual transformer, and real-time makeup transfer. And also this year's CVPR work on self-supervised landmarks estimation. This paper will be presented on Wednesday. The self-supervised landmarks estimation, different from other self-supervised task, often requires an image encoder that learns distinctive features representation in different local regions to best boost the downstream task. Typical existing works usually follow a two-stage training pipeline, where in the first stage, instance levels of self-supervision training is done to learn global features for each image. Firstly, the feature matrices are only learned on the instance level, and the following local regions correspondence calculation through hypercolumns are often expensive to compute. Lastly, the correspondence learning lacks optimization towards more important regions. Intuitively, regions like lip and eye should be paid more attention to in the training process. So to overcome these challenges, we propose a two-stage training framework that learns the local regions. In the first stage, we pre-train a vision transformer-based backbone with positional encoding for each non-overlapping patches. And given an image, we randomly mask out some of the non-overlapping patches. The unmasked patches will be passed through the encoder, and the decoder is trained to recover masked patches. And in the second stage, we first compute a class token here by aggregating patch tokens that represent the global features of the image. The class token is used as the query token, and each patch token is used as the key token to calculate and separate tokens into attentive and inattentive groups. That is, attentive tokens are those corresponding to more important landmarks regions. To make calculation more efficient, we also approximate the features of all non-attentive tokens into clusters and only perform the correspondence training on attentive tokens in the cluster centers. And here's a quick glance of the results. So we reduced the error by 22 to 44% on the landmarks mention, and also 6 to 18% on landmarks detection. And I'd like to thank the main authors, Bangshan and Kerja. Feel free to check out our poster on Wednesday.
Thank you. Maybe due to the time limitation, let's just directly move on to the next speaker. Next speaker cannot make it today, so I'm gonna just share the recorded video.
Hello, I'm Sun Zhaoyang, a PhD student from Wuhan University of Technology, and I am very honored to participate in CVPRS Virtual Try-On Workshop. And this time I report on the topic, what limits the performance of makeup transfer? Here we begin with an introduction to makeup transfer. Given a pair of source and reference face images, the main goal of makeup transfer is to generate an image that simultaneously satisfies the following conditions. One is containing the makeup styles transferred from the reference image. The other is preserving the content details of the source image. The absence of real targets to guide the model training is one of the main problems in makeup transfer. Most existing methods tackle this problem by synthesizing pseudo-ground truths, PGTs. We find that existing methods using the same PGTs yielded very similar results, even though the modeling frameworks varied widely. Therefore, we argue that the quality of PGTs limits the performance of makeup transfer, not the model framework. However, the generated PGTs are often suboptimal and their imprecision will lead to performance degradation. So we attempt to seek the content and makeup style supervision signals from the input images themselves rather than PGTs. We approach this purpose by investigating the frequency characteristics of these two types of information. And we find the main differences of the same face image before and after makeup are concentrated in its low frequency, LF component, while the high frequency, HF component remains almost unchanged. Based on this observation, we determine our assumptions and propose the CSDMT. It realizes makeup transfer by maximizing the consistency of these two types of information. This is our framework for CSDMT, which consists of a semantic correspondence module for semantic alignment and a makeup rendering module for fusing features and generating results. In addition, we propose two loss functions to improve the model performance. One using self-augmented reconstruction to enhance the model robustness, and one using contrast learning to ensure colored fidelity. This is a qualitative comparison. The proposed CSD-MT produces the most precise transferred results with desired makeup information and high-quality content details. This is a quantitative comparison, and our method has yielded good results on a variety of metrics. In ablation study, we keep the network architecture of CSD-MT unchanged and train this model by using the PGT-guided training process, as in PSGAN and SSAT. We can see that the outputs produced by the resulted models are very similar to those of PSGAN and SSAT. This suggests that the transfer performance is heavily influenced by the synthesized PGTs rather than the network structure. We validate the robustness and generalization ability of the model in various scenarios. However, with our assumption, some boundaries of some extreme makeup are treated as content details rather than makeup style in CSD-MT. This is the limitation of our method. Our code is publicly available. Thank you for watching.
Okay, that's the end of the short talks first session, and we're gonna start our next keynote session right away. Thanks to be on time. We will start right away. You can just sit right here, right here. I can help you. Yes. Let me. Okay. Yeah. Maybe you can start introduction.
Sure. Cool. Let me start introducing our next keynote speaker, Ming. So really my pleasure to introduce Ming. Ming is a distinguished faculty at University of Maryland. She's also Amazon scholar, so I get to work very closely with her. And Ming is really really prolific researcher and veteran in the field of simulation, so traditional computer graphics, simulation, computational geometry, and most recently, she's bringing in all those classical methods into new paradigms, such as including diffusion models. So today she's going to inspire us with how do we bring these physics-based methods to virtual trial. So over to you, Ming. Thank you.
Thank you, Sunil. It is a great pleasure to be here and talk a bit about some of the work which I'm very passionate about, which is virtual trial. Sorry. So this journey of working on this virtual trial actually started probably 7 or 8 years ago. And largely because all of us are very busy and we like to shop online, including me. I joke I don't go to supermarket anymore since COVID. I just shop online 100%. And clothing, however, does not work very well. We found that we actually did a study, over 75% of the returns, according to the customers, it's due to fit. That's number one. And there's many other reasons. The fabric is not turning out to be quite they thought, or the fit doesn't quite fit their body. Again, indirectly, it's about fit. Great, thank you. So we really, for those people who are busy and like to buy clothing, but don't want to deal with shopping in the mall. And this also happened when the items you like, they don't have your size. So you can shop all you want. You don't really know whether the size of your size would actually fit you. So that really was the motivation of how we started doing this research. So this is dated back to probably, as I already mentioned, 6, 7, 8 years ago with my former PhD student, Shan Yan, who, by the way, through her journey, going through Google's and now is also with Amazon, we have this vision of just take a single view photograph to help us recover the garment directly and also the body, and then be able to pick another garment and then see how that would look on the same photographs. And so we actually have published our first paper. This was the first of its time by using single view images to generate garments automatically, but also the body as part of the byproduct. And part of this work depends on and actually leveraging off a lot of research that was already done way before us. And there was a huge literature and also a large body of 3D human body scan that was being acquired throughout Europe, Asia, and also in the US, that basically collect these body of different sizes, and we were able to build these parametric model of a human based on a single view image. And so that database and that parameterization enable us to be able to actually leverage that model to automatically estimate what the body will be. But in addition, we also found out there's actually a large garment database online that allow you to basically stitch together common type of garment, like the tops, like a shirt, like a skirt, like dresses, like pants, and so on, and t-shirt. And so by leveraging these large databases of garment type and their sewing patterns, given a single view images, we were able then to automatically figure out what will be the underlying human body that will fit the images that we saw. But we were also able to perform essentially segmentations of the top and the bottom and be able to identify what they are. So this is advances the computer vision that enable us to do this. And then once we identify the kind of the garment we have, we can also retrieve the sewing pattern and automatically generate the 3D garments, and then thereby drape it through physics-based simulation on the bodies. And we can then start tweaking. So the body estimation is an estimation. It actually taking into account of your body parameters, which including the sizes of your body of different limbs, but also poses. So that means that these are all estimation. And so we actually gone through iterative adjustment and simulation. One of the challenges that we had to deal with was material, because different material folds and wrinkle differently. And also, in addition to that, most of our folds that you and the wrinkle you see, depending on your body posture. So this is really truly a joint optimization of multiple parameters, both the human body and the garment simultaneously. And that's basically what we did. Okay, this is what we did in the 2018. We published this paper at ACM Talk in SIGGRAPH, and that was first of its kind. Just to kind of show you the results of what we had. So what we have on the right, on the leftmost, that's the input images. In the middle, it's the estimated body overlay with the recovered garments. And on the right is the recovered body with the recovered garment. Now, you can see they are not always perfect, but they are pretty good considering this was only using a single view images. That was all. And the best part is once we recover that, we can animate. You can have the leg move, the clothes will move automatically with it. We were able to recover the garment material, so you can actually see how the garment moves. It's not discriminating. It works for both male and female bodies. And so it really is a universal solution for virtual try-on. At least this is one of the first kind. And this in particularly, this show you the leftmost is the original images, and the front and the side views and the back view. Same thing with this. Here's more examples where we have the left images, which is photographs, and we were able to automatically, this is really on the wild example, we were able to automatically parse the images taken on the street and pick the customer's selections of the skirt and show her how that skirt will look on her and overlay on top of it what she was wearing. Even better yet, we can show as a wind blow how that might look on her, how would the new skirt will look on her. Now, continuing, we were able to automatically extract the garments. This way, we can also transfer the garment and retarget it onto a different body, a completely different proportion. There's actually a company out there that analyze if you have a different body type, what garments will fit. And they would actually make recommendation based on that. And that was a perfect example. If you want to see whether a garment will fit on you, this is a really quick prototyping tool. And here's another example where we have the original images on the left, the selected garments being worn on top of that original images, and be able to show as the wind blow how that skirt might look. So that was our vision. And so we got really excited, chatting to chatting with Amazon, I later on was able to help bringing some of these idea and vision to Amazon. And we have actually one of the first 3D virtual prototyping, 3D virtual try-on system that is a learning-based system later on. I'll talk about that later. But anyway, so that's kind of where we started. And we got really excited, but what are the challenges? We knew we didn't solve a problem. What we did is we did a proof of concept prototyping. And the algorithm was generating good results, but they are not good enough for productization. And certainly it's not going to solve all the problems that we started. And one of the reasons we want to reduce the, one of the reasons we do the virtual try-on was to return the return rate, was to reduce the return rate. And to do that, you need to have a good, accurate reconstruction of a human body that is robust. But we also need to be able to automatically recover the garment material much more efficiently and quickly, and also be able to recover the geometry of the garment, because not every single garments that we saw was simple garments. And we were really experimenting on simple garments. And so there are some challenges there. And somewhere in between, we recognize the importance of real-time class simulation. So we also look at this problem a bit. And lastly was the rendering, which we actually borrow the learning-based approach. And I'm going to just kind of quickly walk you through our journey of working on several of this problem. And most of this work is done jointly with my former PhD student, Junbang Liang, who is also currently at Amazon. So first problem, let me just say that none of this problem that I'm going to talk about, and I'm going to present a solution, are solved completely. So the hope here is that I can share what we have done, and that all of you who are working in this area can continue to innovate. So one of the first problem is accurate reconstruction of human body. And what we have actually proposed at that time was, instead of single view, can we improve the accuracy by using multiple view? We obviously don't want 360-degree view capturing. That's too expensive. But what's reasonable? Well, side view, front view, maybe back view. And so that was basically what we were looking at, 3 or 4 views. So we have proposed basically a shape-aware human body reconstruction using the parametric model. We use simple for that. You could use actually any parametric model. There is nothing magical there. If you have a database of a human body, you can derive a parametric model. And that continued to be an interesting debate for those of you who are working in that area. And what we did is we have developed, one of the contributions is a scalable multi-view learning framework. It can take any number of RGB images at an inference time. And we also have developed a large synthetic data sets with ground truth parameters. And I do want to emphasize that this is so important because there will never be enough captured data. And we have a lot of models, class simulations, human body simulation that can provide ground truth data with parameters, physical parameters that we know are the ground truth. So those may not be the real world data. They, however, serve as a data set that's great for supervising the neural network. And this enables us to complement the limited data set that we are able to capture from the real world. And so it diversifies your database. It also adds the richness to the data set that you use for training. So at that time, we have mostly 2D or 3D pose from images, mostly skeleton only. The poses and shape are from 3D skin model. They are very, very expensive. So we were really moving toward a more image-based approach, what most people care about in computer vision. And also we're trying to reduce the running time. And we're trying to minimize the human supervision and segmentation and annotation and so on. As I already mentioned, these are our key contributions. So just very quickly, this is an example illustrating how the network works. Essentially what we have is we have multiple view we inputted simultaneously through this cascade of network. Those are basically regression block. And going from each view, we are passing on the information about the image features through each one of the layer of a network. So the image feature is being propagated as we go down the network, and the body parameters are being shared across all view because it's the same body. So it's the same poses. There's no reason why you can't. So the body parameters are being shared across all views. In addition to that, there are things that are intrinsic to each camera view, which is the camera parameters that are also being shared across each view only as you go down the network. And so those are really important. It helps registering the information, being consistent across each view, but also for the whole entire body. Now, we have simulated a large number of plots on all different poses and actions and motion. This data set is available. And we use a combination of CNU mocap data set with various shape variation and claw simulations and render them under different lighting condition. So we basically tried to diversify all these parameters. What was really interesting is I want to highlight a couple of things through this work, is the use of synthetic data sets actually help. So this is a synthetic data set versus baseline without, and we show the improvement here, even for with either single view or with multiple view. What we also have done is that we have compared our approach with just single view with the state of art at that time, that was HMR, and we show that with this approach, it also helped improve the accuracy. The accuracy was being measured in basically mean joint errors and also mean vertex errors. So you can think of it as a Hausdorff distance. And we also compare with a whole bunch of soda methods, and they are shown here with our approach indicating with the lowest error rates in joints. And so the takeaway here is the use of both multiple view, which help reducing the inconsistency due to the view perspective, but also synthetic data, which enrich the training data set. Now, what we have found, particularly the biggest gain that we saw was actually on extreme bodies, basically extremely skinny body or extremely large body. And I hope this is very obvious why, because most of the capture data sets don't capture those easily. And so by able to use the simulated synthetic data, we were able to improve results on these customers who really needs help, because most of the clothes are not designed for them. They are outside of your normal range. And so this is where we can really democratize fitting virtually. And so these are sort of some of the results that we have seen. And we have found you could have very, very skinny customers, but with very curvy body. Those are also not normal. We are able to capture those very well as people on the extremes. So people don't fit under the normal spectrum. Those are the ones that we are able to serve. And in fact, those are the ones who have the most problem, probably return the most clothes. So that was a very, very positive feedback. We also look at capturing different poses, and we found this results that we have were very consistent. So takeaway, summarize, multi-stage, multi-view framework was a plus, and synthetic data sets under all possible lighting condition, all different kind of motion, all different environment, all shape supervision was another plus. And so we are able to generate bodies with all various types of BMI, and we can vary the parameters systematically. That was a huge plus. Now that we know we can do better on reconstruction of human body, and by the way, we have some work most recently on also looking at how various parameters actually affect the body reconstruction. I cannot talk too much about it because it's currently under review. But what we found was if you actually take the body from a different view angle under different lighting conditions, even for different skin tone, you never thought about this, it would actually affect the body reconstruction. So these factors do matters. And so then there's a question, how do you robustify and how do you generalize and transfer the results? And that's, a work that likely will be ongoing. Okay, so next, I want to talk a bit about government material recovery. And as you all know, most of the time when we shop, we like to touch the material. Why? Because material is going to determine how the clothes will drape on your body and also how comfortable they are. Without haptics, you may not be able to feel. But with the help of large language model, you get a sense of what the labeling of the material will be and the kind of fabric that you may have worn before. And so that's definitely one. But what we are looking at was how can we automatically recover the garment material without any language, just recovering fabric material directly from videos. And so what we have done is we develop another learning framework where we generate a video data using physics-based simulation. These data is automatically generated by claw simulation. We can control the material parameters, so we know exactly what are the parameters. We can generate these simulated images, their motion, their wrinkle, you name it, we have the ground truth. So one of the advantages of simulation data is we have 100% ground truth. And that will help us supervise the network. And does not require labeling because it's automatically there. And so we use these synthetic data, but we also use real world data as well. We use a large video capture data from MIT. That's our real world data. Unfortunately, it's very limited. And so it's not as rich as what we can. And also it's just a close draping like this, hanging a piece of cloth, blowing the wind. With ours, you can actually simulate a motion. Okay, so we generate these label video data combined with the real world data. We train them on a deep neural network to predict the material type. We use a combination of CNN and LSTM to determine and classify the material type. And the important things to recognize is that the CNN will give us the image features. We then use those image features through LSTM to look at how these image features move over time. And we learned and classified it along with the material. We learn its material type. We see how these image features move, react to forces, how the shape and wrinkle change time, and the sizes of these image features change. And so we were looking for differential using LSTM. So we use a combination of CNN, extract the image feature, use LSTM to memorize the changes and learn the type of material that's associated with it. We simulate these data using RSIM, and this was actually written by one of my former PhD students, Rahul Naran, while he was postdocing at Berkeley, using our collision detection software library developed while I was at UNC. We have only generated 2 types of parameters that was basically arm bending and wind blowing. We could do more, but the data set will become even bigger. But we did test it on these because bending is a very common motion that we see all the time, and wind blowing is another one for most of the garment. And we have tried also various settings. One of them is meshing. Those of you who have worked on simulation, you know the meshing resolution will affect your simulation outcome. So we also look at the impact of meshing. We look at the type of textures and the texture patterns. We also look at the camera position. So we actually try all these different settings. Now, what was really interesting is that across both scenarios, we saw that this combination give us the highest level of accuracy. We also have tried adaptive resolution as well. And so our best result is actually adaptive resolution, except adaptive resolution is not always as efficient and not always as easy to map to a neural network. We also compared it against the state of art, the best work that we know. And the other thing we compare against is human perception. And what we were shocked was we actually outperformed human perception. And so this was a really positive feedback. All right. So just to kind of give you some idea what a simulation outcome look like. So these are some of the simulation that we have. Arm bending and also hanging the cloth in the wing. And so just different textures, different background, different lighting condition. These are real images that were captured directly used from MIT. The video images was on the left, and our recreated animated fabric is on the right. And right here, we did a material cloning. We have input videos, kind of silky-like, and we show you how it might look as a skirt. We also did another one, which is heavier material, and we show you how that might look as a skirt. So you can imagine this kind of tool will be a tremendous value for the customer. They might like the skirt, they may like the style, but they might want different material. They can do that. All right, so continuing. The result we have was very promising, but we would love to do more because we could do 70, 80% accuracy. It's good, but it's not perfect. And so we have also looking into the differentiable class simulator for material optimization. So I do want to say a few words about this because there has been a lot of interest in the use of differentiable programming, whether it's differentiable physics simulation, differentiable geometry, differentiable vision, differentiable rendering. The idea there is not to learn everything from scratch using only data purely based on data, but also go back to some of the model we already have and then treat the model as one of the network layer. And in this particular case, we treat a physics-based simulation as a network layer. We can compute the gradient, back propagate, use the gradient information can help us optimize much more efficiently, much more quickly. It's like you're already in the manifold where the condition of what you observed might be. And then you can also use this to learn much more efficiently of all kind of phenomena, physical phenomenon events, but also to achieve control. If you want motion control, you want parameter estimation, this is the basic framework that you can do for physical material, for optical material. This is, by the way, very, very widely used by some of my colleagues who work on imaging. And they have seen tremendous success, as well as computational display, trying to design a proper material for display. So this is really like carrying and making an impact across many, many different fields outside of computer vision, also in computational photography, computational imaging, and also computational robotics. So we did develop what we know is the first differentiable class simulation. And basically, we have developed a dynamic collision detection. If you want to think of it, it's continuous collision detection to reduce the collision's dimension. For those of you who have done any kind of simulation, you know, any kind of simulation, collision detection is the most expensive step. And so I will talk a bit about how we do this in the optimization framework. And what we did is we also compute the gradient for these collision response differentiation, and then we back propagate. And we don't just back propagate, we also optimize the back propagation step because cloth simulation is very, very high dimensional computation, especially when you have high resolution to get high accuracy. So what that means is the resulting matrix is going to be very, very high in dimensionality as well. But if you look at the structure of these linear systems, they are actually fairly sparse because every single element is only affecting the neighboring element. So you'll see this small block of a very large matrix with a small blocks of these, non-zero matrix. And the idea there is to use QR decomposition to reduce the dimensionality. So for collision response, we transformed it to a quadratic programming framework. Basically, what we want to do is to minimize the difference between what we simulate and what our target position will be. And the target position could be images, could be whatever observation you may have. And basically, this is what we are doing, is minimizing that differences through this quadratic formulation. And subject to the equation there, where that equation is a linear equation, that's a linear constraint that can be imposed to indicate a single point should not penetrate through a plane. So if you think of a single point could be any body, could be a vertex on any body, a plane could be your cloth, and vice versa. This is how we encode collision detection, is we treat it like a linear constraint. So this means that you have a large number of constraints you have to deal with, you have to solve, right? So you actually can solve the gradients, and the gradient of the collision response is you compute the losses, which is you want to minimize the losses with respect to your vertices and various parameters in your matrix, and also the time steps and so on. I will not go through all the math because it's fairly involved. And then once we solve that, we have a very, very large sets of a matrix for solving the linear systems. And again, this is where we use the QR decomposition to reduce the dimensionalities of these matrices that we have to solve. And the theoretical speed up is shown there. It's actually quite substantial, as you could see. So how well does it work? Well, it works surprisingly well. What we have found was that we were trying to simulate a fairly challenging scenario. Cloth, you crumble together, you throw it into a pyramid, really, really difficult. High number of collision, we were able to significantly improve the overall results by about 2 orders of magnitude with this approach. And at the same time, it reduced the errors that's resulting from the estimation. Because recall, we are using synthetic data, so we know what are the ground truths exactly, because we know what we put in and we know what we are able to recover from the observed render images. Okay, so and materials, it was what we are estimating, and that's what we are trying to measure as the errors. So overall, the result was surprisingly great, but we also found that just kind of give you some idea, you could see the percentage of errors, ours is right here, and the number of sample that we took to do this for this learning-based approach was much, much fewer by comparison against PPO, which is a really well-known packages, which a lot of people use. So just a very quick video demo. This is just for motion control. What we want to do is to pick up a cloth, drape it or drop it into the laundry basket. And with PPO, using a single point mass, we couldn't do it after 10,000 trials. With ours in 53, okay, it get dropped into the basket. It's not completely all optimal. There's things that we could have done in terms of energy minimization, but I hope it gets the point across. Okay, so just in summary, what I have shown here is differentiable physics simulation can provide the kind of gradients that through very efficient backpropagation that you need to learn the dynamics for control, for material estimation, and also model-based RL. This is the direction that we have been currently pursuing independent of the virtual trial. Now, one more thing is user-friendly recovery of the garment geometry. And so that's another area where we have looked at. And basically, we have done all these work, and we started to combine these approach into one. And I won't go into all the detail now, because I'm keeping track of the time. What we did here is we developed, again, a learning-based framework where we are looking at the temporal geometry features to infer the fabric material. And we do this by using an autoencoder to capture and model the garment geometry. And the basic idea here is that we use 2-level autoencoder for the garment. We have a higher level global shape supervision, and then we have a local patches, a group of points. And we are assuming that we have the input as point clouds. And so we are using a combination of both global and local to capture the kind of a geometric detail we like, but also efficiently. So the autoencoder is doing both. And so it is the first, as far as we know, the first parametric garment model that can account for arbitrary topologies for any garments. And very quickly, here is what we have for our network. We have an RGB videos. We process using CNN, very similar to what you're seeing earlier, extract. You can see very naturally, this is an extension of our prior work. We extract the image features, then combine it with the body and garment estimation way back. As I mentioned earlier, we were able to also extract the garment latent code and the human body using the image-based estimation, put it into our 2-level garment decoders. And again, that 2-level was the global overall shape and the local patch fitting. That's very important because the local patch fitting ensure we are also capturing the material property versus the global point cloud. It's ensuring that the overall shape geometry is correctly captured. And these are coupled together. The garment latent code also help us supervise the material estimations, and the output is both the garment meshes and the fabric material. Okay, so this is a basically exact highlight that look at the global geometry and the local patches and how they actually doing the supervision independently. I won't, and in a nested loop. It is important for the global shape estimation for autoencoder and decoder because it captures the low frequency of the shape and it's conditioned based on the human body parameters. So this is coupling back to the geometry of the body as well as the pose. So this is where the global shape supervision is important, but the local one was important to get the geometry correct. Okay, down to the lower level detail. So it's a combination of both that give us the kind of accuracy and efficiency that we want. All right, so the overall network structure is very similar to what you have seen, a combination of CNN plus LSTM, but also with encoder and decoder to capture and recover the exact geometry. We also have a very large simulated data samples. Again, these are all different kind of natural out there in the wild background, and also under different lighting, different daytime. We try to vary the lighting condition and the material property and the poses and motion. And again, with the motion, with this, we're able to get fairly good results. But we did one more thing is we also did a very extensive user study. And we basically have the ground truth on the top and the simulated results or the recovered result on the bottom. We asked the user to score them, to tell us what they think, how close they are. And the scoring system is out there between 0 and 10. And you could see the various poses and different fabric material and what they think. So we were fairly happy compared to all the other methods. This is the one that was able to achieve the best qualitative user perception in terms of the fit accuracy, in terms of recovering accuracy. We have used this to also reconstruct garments of all different type, and these are some of the examples. And what was interesting is we actually tried this on a previously unseen real world video, and it works. So you're actually seeing the patches being recovered as the video moves, and that's at a different level, okay? And these are recover point clouds. As far as the material, which is what we were interested, again, the input video was the simulated data. The right-hand side was the material being cloned and transferred into a moving avatar. And as we change different material, you also notice the fabric material and the garment look differently. And so when you have very stiff material, it does look very stiff on the clone avatar. Now we didn't stop there, and this is actually one of the Amazon employee. And you could see he was our model. he did this at home for us, and we were able to recover the chrome avatar as well as the material. So courtesy of our Amazon colleagues. All right. Last but not least, this is really a virtual trial application where we actually have someone, this is a real video, someone who is moving around. We were able to capture the estimated results and then be able to show you how the simulated result might look like. As you notice, we did not get the rendering completely right, but that was not our focus. And this is really where NERV can actually come in. We have done some more recent work, and we are trying to combine NERV with simulator results as well. So this is one of the first end-to-end model for joint estimation of body and garments, and I'm going to end that part and move on just very quickly. I won't go into all the detail. One of the things that we did was we started looking into a game-based garment recovery, and then be able to actually use simulated data to create a large variations of garments using game-based approach. What this does allow us to do, particularly for designers, is now you can see, you can morph. If you have a garment type, can you automatically morph to a different one? And this is what we think will be really interesting. And we have ability to go back and forth between the 3D product and the 2D sewing pattern. And this is one of the reasons why this could be potentially interesting for the designer. And this will work for all different body shape as well. Just very quickly, I won't go into detail, was we also thought about the simulation code. They are expensive. And can we actually do something different? So just to throw a wild idea out there, most of the simulation parallelization we have seen are based on domain decomposition, which means that you decompose your simulation domain, which means that you decompose the garment you see into patches, and you run the simulation and you're looking into it. An alternative would be a time domain parallelization. And so the basic idea here is to simulate the clothes at very, very low resolution, but you can do this in real time. And you'd like your movie, it just fill in with a gap, with the resolution. And you can do this for rapid apparel prototyping. And we have actually done this, and you can get, what you need to do is fill in this 2-level mesh representation, bridge them. You need to think about workload balancing. You need to think about how do you fill in the missing detail as you do this 2-level simulation. It works. All right. At least based on our earlier try-on, I won't go into all the detail, but we have actually tried it on different garments, and this is the scalability curves. It's nearly linear. And so I thought there is a lot of potential here. So just in case, if anyone is interested, on the left, it's a serial simulation, 70 seconds per frame. Simulation's very costly. I know we have AW service, but if you have to simulate a lot of data, it can get costly. So one possible alternative, I don't think Amazon like this, but you can simulate with a tempo domain decompositions and parallelization. You can do this a lot faster, as you can see. It's almost 100 times faster. Okay, so that's another potential alternative. Obviously, you can also parallelize on GPU as well. But I hope that kind of get people to think a little bit about. These are not simple motion. You know, this is karate motions, you know, people falling, and also ball twisting with lots and lots of self-collision. This is one of the most challenging scenario to simulate. And yet we are able to show with this parallelization in temporal domain, you can actually get 100 times speed up as well. All right, just want to capture very quickly that one of the things for rendering that we have gotten to was to come up with a learning-based framework to visualize how the fit might look. And this is really, really important. It's not just, basically what we're doing is we're simulating the garments on the body of all different shape and different type, and then be able to learn the dynamics of cloth directly from it. So we are using a novel encoder and decoder framework, just like what you saw already. We capture both the global and the local features directly, and also from the input body. And then we develop and design very novel loss function to encode geometric, physics, design, and tailoring constraints. Now, I want to say that this framework is using a semi-supervised framework to integrate dynamical constraint into a deep learning framework. But by the same token, there is tremendous excitement right now about generative AI. And a lot of these generative AI techniques out there, I will not name them, don't have the constraints. You could incorporate, you can do the same thing as we did, by incorporate the geometric and the physical and the design and the tailoring constraint, possibly with user feedback, to actually ensure your generative AI is actually designing something that is physically accurate and correct. And so that is, my advocate without going to all the detail, but I just want to show, we did have a large number of loss function that we have incorporated, and we were able to achieve 1,000 times faster using this learning-based framework, and also remove a lot of, problems. And this just to show you even better yet, you can print texture on it, and we can do this draping all in real time, because when you print the texture, you change the material. With a learning framework like this, it doesn't matter. And the best part, as I already mentioned, we started, most of the time when you buy a garment, you want to know where it sits on your body. Is it above your belly, below, or way too long? And you also want to see where the sleeve sits. This will enable us to see how any garment of different sizes that you purchase will actually look and how you might fit on your body. All right, so I'm going to just end right here with the video at the end. And this is showing you basically with this approach is all learning based, run in real time. You could have different poses. The texture will move with the clothes and all in real time. And we can do this on any body with any graphics design that you printed onto the t-shirt. It's available in Merch by Amazon. All right, I'll end right here.
That was really awesome, Ming. Maybe one question in interest of time.
Yeah.
Do you have a statistics how much of the garments are actually returned? Like you said, 70% of the garment returns are given reason 20 issues. How much of the garments are actually returned? Like
I believe this is statistic way back in 2020, about 76% based on the survey that we have. But again, it's classifying a way based on how you collect.
N number, you sold 100 on Amazon. How many are returned to Amazon saying
That's what I say, 76%.
76% return is correct, or 76% is return?
76% of return was due to the fit. It doesn't fit them. So if we sell 100 garment, we don't know exactly what's the return rate, but my understanding is roughly about 5–10%. It varies depending on the brand and also depending on the garment type, because some garment type people are not as picky. But all these approach I mentioned, they are all great, but I do want to end with a question and a future direction for all of you is scalability. How do we scale this? And I think image-based solution is really the way to go, because it's very, very, very intensive to capture anything other than the photographs that was provided to you by the retail. So I will end right here, and happy to chat with anybody else later on. Okay, thank you. Sorry for the delay.
Thanks.
Okay. Our first presenter is Pratham Mehta from Georgia Tech.
Hello, can you guys hear me? All right, hi everyone. My name is Pratham. I am a researcher with Georgia Tech, and I'll be presenting Mobile Fitting Room. Our first author, Justin, is unable to make it here, so I'll be presenting on his behalf. Mobile Fitting Room leverages on-device machine learning to personalize virtual try-on while preserving user privacy. With this tool, users can select a garment to virtually try on and highlight the area on their body where they want the garment to be placed. The try-on images are then generated on-device for the user to view. So virtual try-on has been a popular topic of research with plenty of applications, and we've seen two overarching approaches. The first one are the classic non-diffusion-based methods such as warping modules. These often fail to simulate realistic lighting conditions such as shadows, wrinkles, and they also often struggle with garment deformation when dealing with complex body poses. We've seen that recent research exploring diffusion models has been very promising, but these run on the cloud due to the high computational demand and storage demand, and this poses privacy risks to the user because you're uploading your private body image data. And also it requires the user to rely on a very strong internet connection in order to send, upload, and receive these images. Which brings us to our main research question. Can we do virtual try-on completely on device? The answer is yes. I'll show you a quick demo of how our application works first, and then we'll get into the technical nitty-gritties of it. So we begin by first selecting a garment. And then once we do that, we select an image upon which we want to generate this garment. After that, we use the paintbrush tool to highlight the region upon which we want to impose, or the region which we want to replace with this garment, as you can see here. Once that is done, we press generate and watch as the model runs on device to generate this new image. We can see this diffusion model is running over 30 steps. And at the end of it, we see this image generated with the person now wearing the garment that they had originally selected. With that, let's talk about the technical pipeline through which we achieve this. The first step in this pipeline is fine-tuning. So we follow the approach from Dreambooth in order to fine-tune Stable Diffusion v15. To do this, we fine-tune the UNet and a text encoder on a small number of reference images of a single garment, along with text prompts containing tokens that uniquely identify this garment in the reference image. This would allow us to use this unique token every time we want to add this garment to a person. This gives us our fine-tuned model, but unfortunately, this model is still too memory, storage, and compute intensive to run on device. Also, it's incompatible with Apple devices as it stands. So the next step in this pipeline becomes compression. In an operation called chunking, we split this fine-tuned UNet into two chunks. This will increase the chance of cache residency and multi-core utilization on the Apple neural engine. Then we follow a process called palletization to further compress the weights. Palletization clusters the model weights and creates a lookup table to the cluster centers, as you can see on the right. This way, the original weight values are replaced with their pointer to the lookup table, which saves size while also retaining accuracy. The final step puts everything together through in-painting, which consists of using the paintbrush, as we saw, to highlight the region on your body. This uses an in-painting module uses a control net to ensure that the diffusion model places the selected garment only within that masked region. And here are some example use cases along with the results. We see that the generated image along with the orange jacket shows that the diffusion process is able to incorporate realism to make its own creases and shadows in the shirt, as we also saw in the demo initially. The generated image with the blue dress on the bottom right shows that by using the in-painting module with diffusion, we're able to extend something that's initially short sleeves, as you can see, into a long sleeve dress. So we get a lot of creative liberty using this combination of the in-painting module along with the diffusion module. So yes, as I just presented, Mobile Fitting Room is a mobile app showcasing on-device virtual try-on. We demonstrate a technical pipeline that considers model efficiency along with user privacy to optimize the virtual try-on experience. Now, I know we're short on time, so I'm going to ask you guys to direct all questions to my email, which is my first name, pratham@gatech.edu. Thank you for your time.
Okay, we may have time for one question if you have until. Otherwise, we're just gonna move on to the next. Oh yeah, go ahead.
There's a library of models technically, and one model is for a government. The user selects the government. Essentially, they are selecting a model, and then wait for a pipeline to generate the answer.
Yes. So for the people online, the question is that you're asking that if we have one model for every single garment. Yes, that is correct. So our current research has a single model for every garment, which exactly, because each fine-tuned model is associated with a particular garment, and based on that unique token from the selected garment, we decide which model to call. Yeah.
Our next speaker is Mehmet Sengin Seyfiloglu from University of Washington. Yes.
Hi, everyone. My name is Saigun, and today I'll be presenting Diffuse to Choose from my last internship at Amazon. So in this work, we aim to achieve virtual try all, which means that we want the users to try any kind of product in any setting, whether it be garments or furniture or any sort of accessories. For virtual trial model to be effective, it must fulfill the following 3 criteria. First, it should be able to operate any in the wild images with any background. And second, it should preserve all the fine-grained details of the product item while also harmoniously integrating it into the scene. And third, since we are going to be serving this to billions of people, it should be very fast on inference. So previously, we proposed Dream Paint, which is the abbreviation of Dream Boot in Paint for virtual trial, which is basically just Dream Boot in a mask setting. For those who don't know, what we do here is that we take a small amount of photos of the product that we want to try, and then we fine-tune a diffusion model in a few shot setting, and then integrate this new token into the models dictionary. And then we can later use this to in-paint the region. However, this is a little bit different than Dream Boot as we are using the mask regions, so the model can in-paint later on. This model is very good in painting the regions for virtual trial. As you can see in this examples, it can in-paint wall arts or some even weird Roman armor. So it fulfills the first 2 criteria. However, it fails on number 3, which is fast inference. As you know, Dream Boot requires few shot fine-tuning for every product, which is very slow and almost impossible to scale. Second algorithm is paint by example that we used. This was published in last year's CVPR. It's very simple. Instead of using text conditioning, they propose using image conditioning like this. So it's very suitable for our case, where we have some source image, we have a mask for the garment and the reference garment as an image. And what they do is they use this image encoder and multilayer perceptron, and then just relay the CLS token from this reference image to guide this diffusion process to in-paint the region. We trained this paint by example with our own virtual trial data set, which is in the scale of millions. However, as you can see, since it relies on high-level features or image embeddings, it kind of like on a high level, it resembles the item, but fails to keep the fine-grained details of the item. Can we upgrade this approach? Like, since they're using just CLS token and basic image encoding, there are a lot of ways we can upgrade this. For example, we can improve this. Instead of using CLS token, we can use all the clip embeddings or patches, or we can use a larger image encoder. We did exactly that, but no matter what we do, paint by example keeps omitting fine-grained information from the reference images. As you can see, using all the clip patches, it can somehow somewhat infer some details. Using a larger image encoder, it can get the textures and such, but it still fails and can't do it properly. So we just finalized our idea that it can't fulfill our criteria, especially number 2. So what to do? So we need some sort of pixel level signal from the reference image alongside the image conditioning to guide this process. Enter diffuse to choose. It's very similar to paint by example on the left-hand side where we have the reference. It is guiding the diffusion process. However, just to guide this process with the pixel level signal on this hint channel that we call, we use an additional unit where we are just stitching this reference image inside the mask region, and then we are relaying this pixel level signal. So we're not using variational autoencoder on, oops, sorry. We are not using variational autoencoder on this hint signal. It's purely pixel level, and we are using a shallow adapter module to bring it to the resolution of this unit expected feature maps, which is 4 times 64 times 64, I guess. And then this pixel level hint signal is then modulated using super basic feature-wise linear modulation layer to every skip connection of our unit, a main unit encoder. So what we do is we just relay this pixel level signal with a linear modulation on a channel wise, and then it helps drastically for this in-painting process. And when we compare against all the PBE variants, we beat them in clip score and FID. We then compare against DreamPaint. Mind you, it's a few shot fine-tuning model, so it takes about 40 minutes for each item to be fine-tuned, and ours is 0 shot once it's trained. You can check the results just to save time. We're almost on par with DreamPaint on similarity and semantic blending metrics that we conducted with human study. And some results, which I will provide QR code at the end in our project page, which you can check later. Some more results. And you can do some cool masking tricks where if you draw the mask like this, the model can infer that the t-shirt should not be tucked in. If you draw it like this, it will tuck the t-shirt in, or it can, roll up sleeves and so on and so forth by controlling the mask. Or you can iteratively decorate the room by, easily adding an item at a time, or iteratively combine clothes for different combinations. Yeah, so thanks to my collaborators, and thank you for your attention. Thank you. Do I have any time for demo? No?
Is it short?
I don't know.
Maybe later.
Okay.
We don't have time, sorry.
Right.
Okay. But any question, yeah. During the setting.
Yeah, it is size agnostic. Sometimes, for example, especially for furniture, it fits things where it shouldn't be fitting. So it's more, yeah, I guess it's size agnostic. That's the problem with this model. Yeah, that's the next step we're going to do. Definitely can be done as another conditioning factor. Yeah. Should I take another question? Or we currently don't.
No.
For the next step, it's an ongoing debate still. We haven't decided yet, but in Amazon there are many models, especially for the certain sizes, or we have that kind of data.
Okay. Our next speaker is Chae-Ring Kong from NXN Labs.
Okay. Hi, I'm Charon from NXN Labs, and since I'm not here to introduce a technical paper, but to just share some of our learnings and endeavors as an early stage startup operating at the forefront of fashion AI, I'll try to make my talk as lighthearted as possible. So today I'm trying to talk about this topic, integrating learning-based VTOs, its challenges and advances. Okay. So as you guys here in this room are all familiar with, virtual try-on has witnessed impressive advances in the recent years, as is the case with general image generation technologies, thanks to some foundation models like Stable Diffusion. However, we believe that there are still remaining challenges. So I came up with 3, but I'm sure there are more. So first of all, it is hyperfidelity, that is preserving the garment details beyond what LPIPs can see. And second is image aesthetics, which is producing not only accurate, but also attractive images. And lastly, style diversity, as in serving clients with different tone and manner. So let me start with a quick question. This is a typical virtual try-on task. So we're given a garment image and a try-on result. And what could be wrong with this result? I wanted to ask people, but for the time being, I'll just give out the answers. So there could be many things that could be erroneous in this result, but most iconically, the printing is distorted. So the original garment says love and colors, but the try-on result, the printing is not fully readable. And here's another example. This one is a little more trickier. And again, the answer is the number of buttons, because in the left garment image, there are 5 buttons at the center, but in the try-on image, guess what? We have 6 buttons.
Quick clarification, is this your internal method?
Yep.
This is the internal method.
Yep. Yeah, so the point I'm trying to make is that at this level of granularity that we're operating, at this level of fine-grained details, some of the most commonly used evaluation metrics like LPIPs can totally go blind. So this is our inference on MP LPIPs evaluations of try-on images, which is recently introduced in a paper called Magic Clothing. On the top row, we can see that the right images display clearer logos and better details. However, the MP LPIPs favors the opposite. And on the bottom row, we can see that all 3 try-on images have different printings and different letters printed, but the MP LPIPs outputs almost same scores. So this clearly demonstrates that current evaluation metrics might be insufficient to capture the level of details that we actually need to make this technology practically applicable. And here's another question, which one looks better? We have a pink knitted t-shirts and 2 try-on images. And I know that the colors are a little different, but let's forget it for the moment. And given that, I think the 2 renderings of this pink t-shirt are all decent. They have nice colors and nice set of black buttons at the center. So if someone asks which one looks better, I'd say it's a matter of perspective, which is the case with image aesthetics in general. So when we're serving real-life clients like fashion brands or e-commerce platforms, it is important to deliver not only accurate renderings, but also attractive renderings so as to persuade the customers to make the purchase decision. And in that case, many different factors can chip in, such as like size and fit, try-on style, or even camera works. So I think this is the point where virtual try-on can be really complicated if it is trying to be incorporated to real-life applications. And lastly, this one is a little straightforward, which is style diversity. So our clients have their own unique tone and manner. Some brands could be very cheap, others could be friendly and approachable. But so far, our publicly available data sets like VTO and HD, dress code, and stuff lack such diversity. So models primarily trained on these data sets might be unsuitable to support those kind of different needs for style and tone and manner. I would like to wrap up this talk by briefly introducing our approaches. So we admit that it is extremely challenging to produce editorial quality images with like a simple 0-shot feed-forward inference. So we're trying some of our sideways, some of our current research efforts include improving fidelity through retrieval-based fine-tuning with pseudo labels, or trying to support a wider variety of styles with point-based spatial control. And we're trying to enhance efficiency with some of the recent techniques from diffusion distillations. To elaborate on some of them, this is our basic pipeline for retrieval-based fine-tuning. So given a person and a garment, we retrieve the relevant pose, the person images with the relevant pose from our database, and we perform a predefined working on that retrieved person images to make pseudo labels, and we fine-tune our model on those images. And on the bottom row, we can see that with only a lightweight fine-tuning, our result improves greatly, especially in terms of the details. And this is our point-based spatial control. So we are combining the diffusion features with some positional embedding techniques to obtain one-on-one correspondence from the garment image to the person image. And we're trying to achieve point-based controls so that we can control like the sleeve length or the overall fit of the try-on image with these point interface. And the bottom row shows some of the preliminary results. Okay, so I made this talk really brief for the time being, but we would really welcome further discussions. So feel free to contact us for more discussions. Thank you.
Thank you. We have time for one question, if you have any. Otherwise, we're gonna move on. Yeah. Our next speaker is Jung-Ho Kim from KAIST.
The main objective is to create realistic and natural human images wearing a given clothing item. And the main point is to preserve the details of the clothing, such as logos or text. So for reference, you can use your own human images in this demo page. So you can try the virtual trial in real time. So in recent years, the stable diffusion based on the latent diffusion model has revolutionized the image generative model field. So this has led to the foundation model virtual try-on methods such as DCI VTO or Light VTO. So the main advantage is the generalized performance for the use of pre-trained knowledge of the foundation model. So the game-based model trained from the scratch shows severe performance degradation on different data set, and fine-tuned on stable diffusion 1.5 shows some unnatural images on different data set. So there are some limitations in existing method. The first is radical inference approaches of closing tokenization into text loses some spatial information due to the excessive spatial information. And second is DCI VTO approach, which are use warped closing into the model input so that they cannot be addressed miscorrect warped regions. So we first attempt to use control net, which shows promising results in the aligned condition. So, however, the generative results in this figure show that control net still lacks to preserve the details of the clothing. So we believe that this is the limitations of the add operation of the control net. So this is the overview of our stable VTO. So we introduce the zero cross attention block into the existing stable diffusion, and in this attention mechanism, the query is the person, and the key and value is the closing. So we kept the stable diffusion frozen, and initialize the last linear layer of the zero cross attention block with zero attention. So, and we propose, we first apply the data augmentation technique for the virtual try-on and propose a novel attention total variation loss, but I'll skip the details of the method. So as we add one by one, we can observe that the attention scores more converged so that the details of the closing were clear. And this is the visualization of the attention map of the zero cross attention. So as the query moves to the right, and the key with highest attention score also moves to the right, so that this is indicating that warping occurs on patchwise spaces. And this is the results of our method. Stable Python enables natural and accurate virtual try-on. And we propose firstly a single data set evaluation, and second is cross data set evaluation for the measure the generalized performance. So we can see that our method shows very promising results on both settings. Thank you for listening.
Okay, any question? Okay, then maybe we're gonna move on to the next final speaker. I'm sorry. Jung, can you unshare your screen? Stop the sharing. And our final speaker is Xingqiao Yang from Cyber Agent and University of Tsukuba.
Hi, my name is for 3D facial makeup estimation and applications. This work aims to enhance the capability of 3D multiple model in accurately representing makeup, a crucial aspect of digital human as well as visual try-on. The 3D multiple model or 3D MM is widely used in various face-related tasks. While lacks comprehensive makeup representation, our objective is to extend the 3D MM by developing robust and efficient makeup preview models. This will allow for more realistic and versatile applications such as makeups, 3D face reconstruction, and 3D makeup transfer. Our contributions are as follows. First, we developed two makeup preview models, a PCA-based linear model and a Stylion 2-based generative model. Second, our models are robust in 3D makeup estimation and significantly reduce computational time. Third, this model enables advanced 3D makeup face reconstruction, user-friendly editing, makeup interpolation, and transfer. Let's take a brief look at our method. Our previous work involved makeup estimation extraction via illumination of via image decomposition. These operations are performed on 3D UV maps. The makeup on the face is combined using alpha blending between the bare skin and the makeup. In this work, we use extracted makeup layers here to construct a 4-channel RGBA model, which includes two types of makeup preview models. The PC model, which is efficient and capture broad makeup features, and the Stylion 2 model, which offers high fidelity and captures detailed makeup features. Our makeup estimation network consists of 3 key modules. First, the reconstruction module uses the flame model and the pre-trained 3D face reconstruction network to obtain the 3D shape and the bare skin texture. Second, the makeup estimation module is tailored to the chosen preview model. It is either PCA or Saigon to estimate the coefficient of query models. We also refined the Saigon 2 model by optimizing its coefficients using additional loss functions. So the makeup consistent module is based on makeup transfer and ensures consistent makeup estimation. This is achieved by maintaining consistent inference results even when the same makeup is transferred across different phases. Our modules demonstrate robustness and accuracy in handling self-occluded phases during 3D makeup estimation. The results of previous methods are unstable and have many artifacts. For example, you can see some makeup disappears. This robustness is important for subsequent applications. In 3D face reconstruction task, the PC model effectively restore broad makeup parts, while the Saigon 2 model precisely recovers complex makeup features. We are able to restore even complex makeup, such as gradient eyeshadow. Our model can be simulated incorporated into other model-based 3D face reconstruction methods like Gala, enhancing their performance. We conduct a quantitative evaluation on the 3D face reconstruction text using makeup dataset. We combine the integrating our proposed method into data improves reconstruction accuracy. PC can be enhanced, and we found that Saigon 2 achieve the highest accuracy. Our Saigon 2 model facilitates both full and partial makeup interpolation. The top row shows the results of a full makeup interpolation, blending eyeshadow and lipstick. The bottom row illustrates partial makeup interpolation through style mixing. Here we keep the lipstick color and change only the eyeshadow. In makeup transfer, our model ensure accurate and reliable transfer of makeup between different 3D faces, making them highly suitable for virtual try-on scenarios. Thank you. Happy to chat with you at the poster session.
Great, so I'll introduce our last keynote. This will be a recorded talk by Ira. Ira is a full professor of computer science at the University of Washington and a principal scientist at Google. At UW, she directs the UW Reality Lab, and at Google, she built and leads the team responsible for launching innovative AI-powered shopping experiences on Google Search, including virtual try-on, personalized garment generation, and 3D visualization. Ira's research in generative AI has been recognized with numerous awards and publications.
You should share screen.
For inviting me to do the talk in this workshop. I'm very, very excited. Huge apologies that I wasn't able to be here in person, but I created this talk just for you guys, and I will be at 3 p.m. later this week, and so please feel free to find me and talk to me, ask the questions. I would love to chat with anyone who's interested. So I work both at Google and the University of Washington. And my big passion in the last several years is AI fashion. And
Sorry. Oops. Right. You can sound this better. Is this better?
No, it's good. Sound. Yeah. Let's do it.
When you share in Zoom, you have the option to share some.
Okay.
At the moment, you share.
Let me just go back.
Just stop sharing. Stop sharing.
Restart sharing. Okay, let me try that.
Stop sharing. The option.
Share sound here. Okay.
we could do much better in that space. So the ideal experience is, I think, there's like three basic things that we have to create to be able to make it really nice and beautiful and useful experience. Because as we know, shopping is sometimes a necessity, but a lot of the time is a form of just feel good type of thing, entertainment, just distraction, and so on. And so we want to make it as nice and easy for people to do, and not to waste time as well. So there's three big buckets in my opinion. One, you should be able to find pretty easily unique things that you are interested in. Number two, you should be able to visualize anything you're interested in very quickly and beautifully. And number three, if you decided to purchase something, you want to know that it's gonna look great on you, and like be really, you don't have to go through loops of returns and look again and so on. Okay, so let's see where we are right now. In each of those three buckets, in my opinion, we are very far from the ideal experience, and so this is where generative AI and machine learning comes in. So first of all, it's very hard to find and hard to describe things. And so we have a really nice quote here from one of the participants in our big user study, who said that, "I feel that everything I've ever wanted is somewhere out there. It's just a matter of trying to find it." And it's kind of true. In fact, Google's shopping graph has more than 35 billion queries, product listings, and it keeps updating all the time. And it's very, very big. How on earth anyone can find anything there, right? And in terms of visualizing and finding and visualizing, we spend a lot of time scrolling on our phones. Hours and hours of scrolling, looking through some images, videos, influencers, ads, and so on. But wouldn't it be nice if we can somehow quickly, beautifully visualize what we need faster? And on the last kind of topic of should look good on you, we know that apparel specifically is one of the most searched shopping categories. But when you survey people, you realize that 68% of people in our survey, at least, said that it's very difficult to know how clothing will look like on them. 42% don't feel represented by images of models, and 59% dissatisfied with purchase because it looked different on them than expected. So all those things make sense. Okay, so how are we going to solve it? And I'm going to go through 3 different products that we already launched that try to address each of those 3 points. And I'll also talk a little bit about the research that we're doing and kind of like where we're going with all of that. So let's talk about finding that perfect item. Let's say that you want to search on Google for a furry jacket, pink cloud-like. That was my query. Ideally, you can find something that, like I have here in the background here on this slide, right? But I don't think you'll find it, just with usual search. So we built a tool where we created our own shopping specific generative AI model to go from text to image. And on Google search, you can actually try it yourself. On Google search, when you search for something like I just told you, clothing related or it's apparel related, you will see this box with a blue button called Shop with Google AI, and you can click on Generate Images, and it will generate some images based on your query in real time. And then you will get 4 images, which is supposed to correlate what you search for. So in this case, we have a super puffy jacket, blue-green pattern with a high neck. Then you can click on one of those. So the 4 images are fully synthetic, they're not real. Then you can click on one of them, and we use Lens here to find for you matches from real products that you can, maybe you click on one of them and you can purchase if it looks good to you. Another example of how it looks like more dynamically. So you search for something, you see the box, you click on the blue button. In this case, we search for colorful puffer jackets, and we can find metallic ones as well. You click on it, you get your matches, and then you can buy it. So this really this is only the first step, but it's really cool application, in my opinion, of trying to convert our usual text-based search to more visual and help people find items that are similar to what they actually like searching for. Okay, our model is creating, so a little bit of details about the model. We can do many different categories. In this case, I show here four categories examples and the types of images that our model generates. We can see dresses and bags and shoes and jackets and so on. There is a lot. We made it very specific that the model generates for now only lay flat images, and our key goal was to create beautiful images, so something that you will find in a fashion catalog. And so that's kind of where we were pushing our model. Now let's talk about visualization for a second. The second topic that I said that would be good to have as a ideal experience. Let's take shoes as an example. Still, to be able to visualize those shoes, I still need to go through look on many images, right? So ideally, we should be able to do more. And so this is where the second product comes in, where we decided that we want to be able to visualize any shoe out there as a 3D spin, so that people will be able to interact with it and swipe it, kind of see it from all the angles very, very fast and see all the details and so on. And so this is an actual reconstruction from our spin model, something that we already launched, and you can see it on search as well, on Google search. I find this one is just so beautiful and amazing that it's almost unbelievable that our model can create that, but here it goes. The idea is that we are, in this case, 7 images. We can do with less images, but let's say that any product out there, a brand provided or merchant provided, has 7 images for this product, and without knowing anything additional, just the images, so no camera pose, no anything else about those specific shoes, we are able to reconstruct the 3D model of that shoe and show it as a spin from all angles in very high quality and high scale. This is a combination of Nerve plus diffusion. I'm not going to get into the details, but it works amazingly well. So if you go on Google search and you search for anything related to shoes, you'll see little spins like that where you can rotate, you can look from all the angles and so on. And these are automatically generated by our AI model. Here's another, you'll see it in the different parts of Google search when you search for it. So here's another version where they just auto rotate a little bit without swiping options. Some of parts of search allow it to swipe and so on. Lots of really nice comments from people that are using it, and hopefully we'll do more and more, and more beautiful visualizations of items and make it automatically and high quality. A few more examples of the different subcategories of the various shoes. So not only sneakers, but heels and sandals and luxury shoes and simpler shoes and more athletic and so on. One of my favorite examples is the one on the top right there with the red sole and the gold heel, which until recently, I think most people would think that it's impossible to reconstruct with any 3D method from such a small number of photos and fully unconstrained. So really excited about this direction. Okay, to the third part where when we chose something and we want to make sure that whatever we chose would look great on us. Or the way that we started thinking about the product in the space is we said that we want to make sure that it looks good on someone like you, for example. And so you see the little models on the slide, little model images we created an effort to capture many people in with different body shapes, different hairstyles, different sizes, different skin tone, and created a diffusion-based generative AI model that takes in a single photo of a garment, takes in a model image, and is creating how the human will look like in the garment. We call it the virtual try-on feature, and it shows how any clothing will look like on a real model. So you see the same shirt here appearing on the various humans. Very excited about this product. Here's an example of how it looks on search. You can click on any search, choose your favorite model, and see how it looks like on them. All the images are, the garment is synthetically generated for every model. The models are real humans, and it's really cool to see how, I'll show you a few more examples. Really cool to see how the different folds and the wrinkles and the different details of the garment kind of adjust to the new body shape of whoever you chose to see it on. Okay, I'll talk a little bit about the tech, kind of the basic, very high level framework. We actually have a CVPR paper on one of our ML models here as well, called the mix and match paper. So, and I believe even Lu Yang is going to talk in one of the sessions in this workshop about that in more detail. So I'll just give a very quick overview. So the inputs to our model are the top, the bottom, just a segmentation of the bottom garment, top garment. It also gets a very sparse representation of the person that we are interested in. We call it the person agnostic. All of these come with the corresponding pose. And also we have an additional input that you see on the left here, which is the layering input, and that tells us like how long should be the sleeve. Is it supposed to be rolled up? Is it supposed to be tucked in? Is there a outer top, and so on. So a little bit of a text input. All of these go to their corresponding encoders. So the top goes to a garment encoder, and the bottom goes to a garment encoder. Person goes to person encoder. The layering has an embedding. Then the top encoder and the bottom encoder share weights between them. And then all of them are going together to a diffusion transformer, which together with the unit encoder and decoder, we are able to get a beautiful virtual try-on image. This is very basic and obviously basic kind of explanation. Obviously, there's a lot more detail here, but that's kind of the structure. Now, you will notice that the person agnostic representation is very, very sparse. It doesn't have a lot of the person.
And so we have a fine-tuning. We have a fine-tuning process in the end where we are freezing the diffusion transformer and optimizing for person features. Okay, a little bit of results, how it looks like. So the middle person is a person we're going to be trying on. The left tops are showing on the middle person right now. And then we can also change the bottoms. On the right are the different bottoms. And the center, you see how they change on the person in the middle. And again, we can change the tops now and so on. It's a very fun visualization. Okay, a little bit more researchy and kind of far out things, but things that we care about. Obviously, we want to be able to do virtual try-on for anything on Earth. In this example here on the left, I show the person that we want to try on. The middle one is the garment, the dress in this case, and on the right is the result from one of our models. You can see that while the difference in body pose between the two is quite big, we can still see like how the dress beautifully drapes on the new body shape and how it looks like, and so people can get a sense of how it would look on them. A few more examples of dresses. This one is kind of cool. You see different fabric, different material. The middle one is the input. Obviously, the one on the right is the output. The pose is very different, the body shape is different, and you can see how the synthesis shows that the draping and the details. This one is one of my favorites. You can see that the input photo has sleeves that are very kind of folded because of the body pose, but on the right, when we synthesize, we adjust it to the new pose of the person that we're interested in, and it kind of flows and it looks really nice. A different fabric, a different body pose, more more details on the dress, and a little more transparency in this one. So kind of cool to see how the model adjusts to the differences in the different garments. This one shows, so on the left we see the input dress, and the other three images show this dress synthesized on the various people, very different people. This seems to be an amazingly, complicated dress with feathers and, a little gaps in the dress that it's interesting to see how the model adjusts and make sure that the skin tone is still preserved and the dress is visualized correctly on the different people. A very complicated dress here. Again, different body poses. And another example with some more different types of complexity and fabric and so on. Okay, we're also really excited. This is very preliminary and initial, but we're excited about video versions of a virtual trial, and we have initial results there. Here you see the different input garments at the top and the predicted video at the bottom. So yeah, lots of exciting directions that we can come up with in this space. If you're interested in working on any of the video try-on stuff, please talk to us. This is pretty cool that the initial dress is with sparkles, and in our predicted version you can see how the sparkles change with time and so on. Okay, you can the cool part about all of those products is that you can actually try them yourself right on Google search. So if you open your phone or computer and just go to Google, search for things like puffer jacket or Nike shoes or shirts or whatever you want that is related to those queries, you'll probably see our products out there, and hope you enjoy it. I gave a very high level presentation of all of the things that we're working on. There is a lot more there's a lot that goes into, it's a very cool research, and we are inventing our own ML to make all of those to power all of those experiences. But also there is a huge effort that is going on how to build things in a way that it's Google scale, so very large scale. How to make sure that things are high quality at this very big scale. How to make sure that generative AI creates things that are useful as opposed to artifacts and things that are not looking as great. So a lot of really cool work that the team created in this space and built over the last few years. Thank you so much. Thanks for listening. And we are hiring. So if you are interested or you have any questions about the research, please just find me during CPR or just contact me on LinkedIn or X or email. Any of those places work. Thanks so much.
Cool.
Thank you. So thanks all the organizers, starting with Vidya and of course Katie, Hanbul, and then all the, I don't know, any other organizers are here, all the keynote speakers, all invited short talks, and the most important part, all the audience. I think I would say it was a great success. I saw people standing on the around the walls, also waiting outside. So next year, definitely a bigger room, and we'll be back. Thank you so much. Thank you.